Hello. So, it's great to have today's session starting with Ramdas, who probably needs no introduction. He's from CMI, and I'm not going through go through his accomplishments. Instead, I'll give him full time to speak about symplectic geometry of SU2 character varieties and lattice gauge theory, which I suppose I am supposed to know, but I don't know, so I'm going to learn.
Thank you. Can you hear me? Yeah, so I'll be very quick because I want to finish in time. I might finish ahead of time because I tend to rush when I have presentation. Yeah, so there are two phrases there, half of which would be familiar to physicists, the latter half, and the other half to mathematicians, especially differential geometers and topologists. So I have to, so what I have to say about the first is fairly definitive. It is quite nice. It is not incredibly difficult. And what I have to do with the second is fairly, there is a clear point, but I don't know if it will lead to anything. But for whatever it's worth, I want to present it. There is a preprint up on the server. So this is the kind of rough plan of the talk. As we go down the page, it will become more and more physics oriented. So symplectic geometry of the SU2 character variety. So a symplectic manifold is a generalization of what physicists call phase space, the cotangent bundle of configuration space. It's a manifold together with structure so that you can define Poisson brackets of functions. And you can, given a function, you can define the corresponding Hamiltonian flow. So all the formalism of Hamiltonian mechanics holds on such a manifold. There is a symplectic manifold which has become quite central over the past few decades. In its algebraic geometric avatar, it was actually discovered in India by Narasimhan and Seshadri. This is the moduli space of stable bundles on a Riemann surface. But it was sort of later realized that it's a symplectic manifold of interest in its own right. And that is the SU2 character variety that I'm talking about. For any compact Lie group, you can have the corresponding character variety. I'm interested in the case of the Lie group SU2. Yeah, so let sigma be a surface. By a surface, I mean a real surface. You will see pictures soon of genus. Genus is the number of holes in the surface. And I take the flat SU2 gauge fields on sigma. For mathematicians, these are connections on the trivial SU2 principal bundle which are flat. And G is the space of gauge transformations which acts on the space of connections. The subscript F means these I consider flat connections, curvature 0. So this, even though the space of connections itself is infinite dimensional, after you take the quotient, this is a symplectic manifold with some mild singularities of dimension that depends on the number of holes. It's 6 times G minus 1. So as a symplectic manifold, there is a corresponding volume element, the symplectic volume element, which is preserved by any Hamiltonian flow. That's Liouville's theorem. And because it's essentially compact, this volume is actually finite. And we will assume that by dividing by a constant, it's actually unit. The total volume is 1. So we are, in some sense, talking about probability measures. So now, supposing I have a loop on the surface, and since we are talking about connections, given any loop, I can parallel transport around the loop, so I get an element of SU2, and I can take the trace of that, and that's a function that depends on, if I fix a loop, it's a function on the space of connections. It's gauge invariant, so it becomes a function on the symplectic manifold, and this is sometimes called the Wilson loop function. And it's a function with values in -1, 1, so I can define a real valued function with values in 0, 1. There is some ambiguity at either ends, but we forget about that. That's like choosing a branch of cos. And so, so what you have to take from this is that given any closed loop on the surface, I get a function on my 6 times G minus 1 dimensional symplectic manifold. And this is called the Wilson loop functional, depending on that loop. Now, supposing I'm given a number of disjoint loops. Now, if one loop can be continuously deformed into the other, the holonomy does not change, so the function does not change. So we have to consider loops which are actually cannot be distorted into another. And we will assume that they are non-intersecting. And then it's an interesting fact that you can't find arbitrarily large numbers of such loops. The maximum number is half the dimension of your symplectic manifold. So if the given G, you can find 3 times G minus 1 such loops. If I start with L loops, I can add more to them until I reach 3G minus 1. So this is not coincidental. My symplectic phase space has dimension 6G minus 1, and I can find in many different ways half the number of loops and therefore half the number of such functions on the symplectic manifold. Those of you who are familiar with integrability would already smell something here, and it's true. This is like an integrable system. The Hamiltonian flows corresponding to these loops divide the symplectic manifold generically into nice tori of dimension 3G minus 1, 3 times G minus 1. So so this is a very, very nice integrable system. Now, there is some, so here is let me give you a picture. I'm going back. I don't know what's happening here. Oh, sorry. How do I go to the top? Yeah. Sorry about that. Yeah. I will come back to the previous page. So here is just to give some flesh on this. Here is genus 7 surface. So you see 6 holes, but there's an additional hole, the big one. So the genus of this surface is 7. Here is the maximum number of one maximal set of disjoint loops, which give you 18 loops. And you notice that if I look at the region between 3 of these loops, they form what is called a pair of pans. So one of these loops is a waist, and then the other things are the legs of the pans, and these are given by, so you have a certain number of pans stitched together in a certain way, and this is called a pans decomposition of the surface. And these spans decomposition, oops, sorry, can be encoded in a graph with a vertex for each of the pair of pans, and two vertices are joined if the corresponding pans share a common boundary. So here is the corresponding what's called the Trinian graph. So what you have to remember, I have a start with the genus G surface. Associated with that, there is a symplectic manifold, the character variety. If I choose a Pan's decomposition of the surface, or equivalently a maximal set of non-intersecting loops, that is on the one hand encoded by the corresponding graph, and at the same time that gives you an integrable system on this symplectic manifold, which divides it into beautiful tori. So just keep that picture in mind. Let me go back. Sorry? No, there is an edge for each shared boundary. She connect a shared boundary. Thank you. Very good. Now, here is the picture. And this is largely due to William Goldman and then the pair Jeffrey Weitzman, that there is this famous theorem in symplectic geometry called the Dijkstraat-Heckman theorem, which tells you, okay, this is a theorem that even if you don't understand anything else of this talk or forget everything, this is your take home. If I have a compact symplectic manifold of dimension capital 2n, and you have n commuting vector fields on Hamiltonian vector fields on this symplectic manifold, each of which generates an action of the unit circle. So then if you take the corresponding Hamiltonians, you remember the numerology. Dimension is 2n, and I have two capital N, and I have capital N functions. So that means I have a map function from this 2n dimensional symplectic manifold into capital N copies of the real numbers, the n dimensional real vector space R to the n. On the symplectic manifold, I have the Liouville volume. So I can do what the mathematicians call push forward of this volume measure by this map. That basically means that you assign to every tiny volume set in R to the n the volume of the inverse image of that with respect to this map. So this is called the push forward map of the volume. And the theorem of Dijkstraat-Heckman, a special case, tells you that the image of this map is actually a polyhedron, and the push forward measure is just the standard measure on R to the capital N restricted to this polyhedron. So the very complicated Liouville measure on this capital 2n dimensional symplectic manifold under this push forward becomes just the standard measure on some polyhedron in R to the n. Now, what is the significance of that? If I have any function on the symplectic manifold which only depends on this capital N variables, if I want to evaluate the integral on the symplectic manifold, I can remember this only depends on this capital N variable. So it's actually a function on this R to the n pulled back. So I can just restrict that function to this polyhedron and integrate on that polyhedron with respect to the standard stupid measure. If I can handle the geometry of the polyhedron, I can do the integration on the symplectic manifold. So this is the wonderful theorem of Dijkstraat-Heckman. It has infinitely many applications. And so this actually applies here. So as I said, even if you take this away, you would have, I would have. Okay, so now the point is, where was I? Yeah, so there is this Goldman, Jeffrey Weitzman work that actually talks about this specific situation. Take the character variety, look at these maps. Then the image is a very explicitly described polyhedron that I will, polytope that I will describe in the next this thing. And as I said, the implication is that if I take any function of these 3g minus 1 variables and I want to integrate on the symplectic manifold, on the character variety, I can just integrate it on the polyhedron, on the polytope. Now, the description of the polytope. How do I describe the polytope? It is described in terms of the Trinian graph. The variables that I am talking about are attached to each edge of the graph, and they each vary from 0 to 1, with the constraint that whenever 3 edges meet at a point at a vertex of the graph, the corresponding variables T1, T2, T3 are obey that spherical triangle equality there. Okay, and one of the key results of my work, which builds on insights from what's called the Verlinde algebra, is that if you take the characteristic function of this polytope in the three-dimensional cube, it has this triple sign expansion that you see there. Okay, that is a key insight. As far as I know, this is not known before, and it is of tremendous use in computations. How much time do I have? Yeah, I have 14 minutes. So let us now compute. I will not actually compute. We can ask, supposing I take n of these loops and look at the product of the corresponding functions, what is the joint distribution of those with respect to this probability measure? In particular, what is the distribution of one of these loops? And you can, thanks to that identity that I put up before, you can actually compute it as a function of the genus, which for some reason here it's called B and not G, and it is that ratio. And when B tends to infinity, that G should be B or B should be G, it tends to this distribution. Forget that f here, that is just a test function. It tends to the distribution 2 sine squared pi t1 as a distribution on the unit interval 0, 1. Those who know the Weil measure on SU2 will recognize this. Okay? So even though for finite G it is a complicated ratio, in the limit of large G, out of nowhere you get the Weil measure on the unit interval. So now I come to the lattice theory on a graph. So let lambda be a finite connected graph, which for later reasons, for physics reasons, we'll call a lattice. And supposing I'm given a certain number of closed loops called plaquettes. So I've shown those red loops are the plaquettes. So in lattice gauge theory, one is interested in a measure on the space of lattice gauge fields modulo gauge transformation. What is a lattice gauge field? A lattice gauge field is on a graph is a function from the edges of the graph to a group, in this case SU2, in such a way that if I reverse the orientation of the vertex, the element of the group becomes its inverse. So on the space of lattice gauge fields, there is obvious measure, the product per Haar measures on each of these copies of the group. And lattice gauge theory integrals are of this kind. You take the Haar measure on the product of groups, and you have a weight function that looks like that, which I will not go into. And in lattice gauge theory, one is interested in integrals of that kind. So now, what do you connect the world of graphs with the world of surfaces? You can do something fairly canonical. Given a graph, you embed it in some three-dimensional manifold. It doesn't matter. You can embed it in R3, and you can take a small of cumular neighborhood and take its boundary, and that is a surface, and that's kind of uniquely determined up to, topologically it's uniquely determined. So, and the graph sits inside as what is called the spine of this manifold with boundary. So first of all, by taking a small neighborhood, you get a manifold with boundary, 3 manifold. The boundary is the surface that you are talking about. So this is the link between a graph and a surface. So the graph is the black thing that's called the spine of this 3 manifold, and the boundary is the corresponding surface. So supposing we can lift your plaquettes to closed loops on the surface so that they are mutually non-intersecting. This is not always possible, but it will be possible in at least one very interesting case, which I will show you. I'm skipping over all this. So now here is the crux of the matter. So we have evidence that in the large lambda limit, when the size of the lattice becomes very large, integration over the characteristic with respect to the Liouville measure approximates lattice gauge theoretic integrals, which physicists would understand if they are familiar with it. Mathematicians, I've given such a rush job that I'm afraid that you probably haven't gotten the gist of it. So there is fairly strong evidence that in the limit of large lambda, you can replicate lattice gauge theory integrals in terms of this model on corresponding integrals on symplectic character varieties. And as I said before, for integrals of these objects on character varieties, there is a very beautiful formalism available called the Doiström-Heckman formalism. Now, to put a little flesh on this, let me consider a case of physics interest, namely the three-dimensional periodic lattice. So in this case, the graph is this trellis of black lines. You should imagine that it's made periodic in all three directions. And I have shown two of the closed loops, two plaquettes that will figure in the action. There are many of them. There are actually 6 of them corresponding to each cube here. Of course, each of these things is shared between 2 cubes. So there are 3 times n plaquettes, where n is the number of vertices here. Now, if you pump up the lattice, the corresponding surface looks like this, the surface of this object. And I've shown you the 2, so here remember, there were these 2 plaquettes. If you lift them to the surface, I hope you can see the 2 red squares, one like this and one like this. Now, we need to, so these give you a certain number of non-intersecting loops on the surface, but we need to add some more to them so that I get the maximum number, which is 3 times g minus 1. I've not told you what the genus is here. And to understand that, you have to kind of look at the dual picture, in which case the plaquettes that are already in place are the ones in red, and then you have to add these plaquettes which are in blue, these blue closed loops also. Once you do that at every vertex of this dual picture, you get a complete set of loops. And here is the corresponding Trinian graph. And if you contract the blue edges, you get this cubic lattice. Okay, so now I'm going to lose everybody here, except hopefully 1 or 2 physicists. So in lattice gauge theory, one of the primary starting objects is what's called the partition function, which is the following. So this is generally the case in quantum field theory. So when you have a discretized version of quantum field theory, you have a naive measure, which is the analog of the Liouville measure. And then you have something called the action, and you exponentiate the action. So now you have the naive measure times the exponential of the action, and the integral of this is called the partition function. And for all theoretical investigations, you need to have control. First of all, in field theory, these are horribly ill-defined. You make this defined by making the number of variables finite by first putting your system in a finite box and then discretizing space-time, which is what lattice gauge theory accomplishes. Once you do that, at least you can define this thing called the partition function. But to get control over all the kind of limits that you want to do, infinite volume, ultraviolet, you need to have good control over this thing called the partition function. And it has been a bane in lattice gauge series that these integrals are defined on a fairly large and ill-defined space with a large group of gauge transformations acting on it, so that the partition functions are very hard to write down, let alone manipulate and analyze as an analyst would do, because you need to have serious analysis on this to control the limits that you want to control. So the advantage of all this is that the symplectic versions of this are, thanks to the Doistermaat-Heckman formalism, give you expressions for the symplectic partition function of this kind, where it's complicated, but among its many virtues is that it's a series with non-negative terms, in fact positive terms. So anyone who does analysis knows that if you are going to estimate, it's better to have things with, without cancellations, without cancellations between positive and negative terms. And so this has that virtue. Then the other big question in the field is the behavior of Wilson loops as the radius of the loops becomes very large. There are similar expressions using the symplectic formalism for those. And if there is an analog, you can, those expressions also have this virtue that these involve series with positive terms. Okay? So there is a large, there is a significant hope that these are more amenable to analytic explorations of the theory. I think I have, I have come in under the time, so I have time for questions. Let me see if, so as I said, there are similar expressions for plaquette-plaquette correlations. So if you take two plaquettes, look at the Wilson loop for one, take the Wilson loop the other, take the correlation of these. How does this behave as the distance between the plaquettes becomes very large? This is a way of testing for what's called confinement. And there are expressions for those. There is something called the Tohoft loop in the industry, where again there are similar things. Now, you can ask what happens in dimension 2. In dimension 2, the theory is solvable in many ways. One of the solutions goes back to a paper of Gross and Witten, and in fact, one can recover those expressions from this point of view. In d equal to 4, there are some issues to be sorted out, topological. Can you add lattice fermions? It seems possible, but for that, you have to introduce complex structures on the surface, which I have not pursued seriously, but I see a way of doing it. I think that's it. Okay, thank you.
So our next speaker is Vikram, and he's going to talk about automata and transcendence.
Can everyone hear me? Yeah? I'm audible? Yeah, thank you. So, yeah, thank you, Dishant, and I'd like to thank the organizers for this opportunity actually a forced opportunity. So, so I'd like to pay them in kind. If you find errors in the talk, you are most welcome to collect some money from the organizers, especially Arijit maybe, okay, of your choice of denomination. Okay. So, so the title of the talk is Automata and Transcendence. There are two parts, and it's a tribute to math science because these two things, this is a place where I came to learn of these two aspects, and it seems appropriate because these two things, the computation and the number theory part, this is one of the institute where we have both of them. Okay. So the best people in both of them. So I've learned a few of these things in the last few years, and I like to give this as a tribute to math science. So we'll be talking about numbers. So we are all familiar with numbers, different kinds of numbers, natural numbers, rationals, reals, and complex numbers. For most part of this talk, I'll be concerned with real numbers only. Yeah? So when we talk of numbers, we want to not only we want to be able to compute with them, right? So and if you want to compute with numbers, you should be able to express them, right? Represent them. So we are familiar with different kinds of representations. So we have so these are symbols for numbers really on the left, and these are the standard decimal representations, the binary representation, and if you wish, the continued fraction expansion of some of these numbers. Yeah. Okay. So so what is a representation for a number? It's a injective map, reals again, to an infinite set of strings on an alphabet. For this talk, the alphabet will always be the binary alphabet, 0 or 1. Okay. So there is some map that maps real numbers to these infinite strings of zeros and ones. Okay. And for any meaningful representation, we should be able to carry the arithmetic structure of the real numbers over to this representation. So what does that mean? So we should be able to add these representations, multiply these, and get the corresponding real numbers. Okay. So since my background is from computer science, so I'll be concerned about the computational aspect of these numbers, right? So any computation that we can do, our algorithms can only work in finite amount of time and space, right? So that means the numbers that we can work with really is a subset of the reals. These are called the computable numbers, and these were defined by, in some sense, by Turing in his famous paper. Yeah, real numbers whose expressions as a decimal are calculable by finite means. So what does that mean? So precisely it means that if you are given some real number and a natural number n, you should be able to compute the nth bit of this real number in some finite amount of time. Okay. So you can put a fine point. The nth bit may not be well defined, but let's assume it is. Yeah. Okay. So a simple diagonalization argument by Cantor would say that most of the real numbers are not computable. That's fine. There is sufficient number of computable numbers, and we all work with them on a daily basis. So when we talk about computation, we also have to define our model, machine model. So what are we going to work with, compute with these numbers on? What machine we are going to use? So in decreasing order of strength, you have the Turing machines, you have pushed-on automatas, and you have finite automata. Okay, and what I'll focus on mostly in this talk are finite automata. Okay, numbers that can be computed on a finite automata. These are called the automatic numbers. Or we can call them francophone numbers, because apparently the literature is full of French people who work on these things, or people who like to speak French. Okay. So informally speaking, an automatic number is a real number whose nth bit is computable by a finite automata. Okay. So let's recall a finite automata. It's a standard interview question in computer science. It's a quintuple. Yeah, we have a finite set of states here. So it's a directed graph which looks like this, a finite set of states. So here we have two states. We have input symbol, we have this alphabet. In our case, it's always 0 and 1. The heart of the automata is this transition function, these direction on these edges. So what happens when on this state you see the input 0, you stay here. If you see a 1, you go to the state Q1. Yeah, and similarly on Q1, if you see a 0, you stay here. If you see a 1, you come back to Q0. So Q0 is the initial starting state, and you have a set of subset of states is an accepting state. So here only one of these states is an accepting state. So there is, with a finite automata, you have a language which is accepted by that automata. So all the strings you read from right to left, and there are strings that take you from the initial state and you land up on the final state. So for instance, if you see a 1 here, from Q0 you will go to Q1, which is the final state, so you will accept 1. If you see 1, 0, so on 0 you will stay here, 1 you go to Q1, 1, 0, 0, so you will read 0, 0, 1, so 0, 0 and 1 you again go to Q1. So it's not hard to see that all strings which have an odd number of 1s will take you from the initial state to the final state. Okay? And if you treat these strings as the binary representation of numbers, then these are the corresponding numbers, right? So this is the binary representation of 1, this is the binary representation of 2, 4, 7, and so on. Okay? So all numbers whose binary representation have an odd number of 1s is basically the language accepted by this automata. Okay, I'm forgetting the leading zeros because for binary representation that doesn't make much sense. Okay. So this is the finite automata. How do we define the corresponding automatic number? So you forget about the final state, and instead of a final state, you have a function that assigns a symbol from your alphabet to each state. So something like this. So Q0 is assigned 0, Q1 is assigned 1. Okay. And the idea is the same. You read the binary string of, so the numbers n, given any number n, you read its binary string, feed it as input to your automata, and if it ends at 0, you output the nth bit as 0. If it outputs, it stops at 1, you output the nth bit as 1. So here is the nth bit of this number. The corresponding number will always start with behind the binary decimal. Okay, so it's half plus 1/4 plus so on 1/16. Then so this is the corresponding number. Okay, so this particular number is called the Thue-Morse number or Thue-Morse sequence. So I'll often switch between the number and the sequence. Okay, so the number is this in this binary representation. The sequence is just a string of zeros and ones that correspond to the bits of that number. Okay. So this is an example of an automatic number. I hope this is clear. The definition of an automatic number. Yeah. So it's a finite so numbers that you can compute in finite amount of time. So here is another example, Fredholm number. Here the nth, 2 raised to nth bit, so all the powers of 2, that bit is 1. Okay, if you see exactly 1, 1 followed by zeros, you will output 1. Anything else, you output 0. Okay, and another example is this Rudin-Shapiro sequence. Okay. So, so basically, you can take any automata and you can construct a corresponding automatic number. Right? Then similarly, there are many non-automatic numbers. You can take any language which is not regular and consider the corresponding number. So that is a non-automatic number. So for instance, here, if you look at the string, it should be the other way around, 1 followed by 0. So equal number of 1s followed by equal number of zeros. We know that this is not acceptable by a finite automata, and you can't accept this number in finite amount of memory, this string. So the corresponding number, if you look at the strings, the binary representation of strings of this form, that number will not be an automatic number. Okay. Here is a slightly more concrete example. Take the nth bit is 1 if and only if n is a square. If you look at this corresponding sequence, this sequence, then you can argue that this is not an automatic sequence. It's a proof that you can give to your students. I'll not go through the proof. Basically, it's a proof by contradiction that says you take this intersection with this regular language, and there's a structure here, and this number is a square if only if this structure has this form. That means this intersection, if this square was an automatic number or automatic sequence, then so is this sequence automatic. But this is not an automatic sequence because they have equal number of, even number of k's, ones followed by odd number of zeros. So no finite automata can accept this string. So some properties of such numbers, right? So what we have seen is you take any sequence, collect this number of the binary strings where the corresponding entry is 0 and corresponding entry is 1. Then the number is automatic or the sequence is automatic if and only if this set F0 union F1 is a regular set. If there is a finite automata that accepts this set. Okay. You can perturb some finite amount of entries in this sequence. You can change them, and even then you will get an automatic sequence. So anything that you can do in finite amount of time, that will remain automatic. Okay. Here is an interesting example. If you have a sequence which is periodic, right? So you have some finite string t which repeats itself. There may be some initial part, but some finite initial part, but followed by a string of length t which repeats itself. Then even that sequence is automatic. and roughly this is the automata that computes this number. So it's an automata of size t, you have t states, and you output these symbols, and the transition function is captured by this arithmetic here. Okay. So what this means is all rational numbers are automatic numbers. Yeah? Because all rational numbers, the binary representation of all rational numbers is ultimately periodic, and since it's ultimately periodic, it has an automata that will accept it. Okay. So you can ask, what if I change my base? What if you go from base 2, which is what we have been talking about, to say decimal? Then also you can define the same concept. For every base you can define. Yeah? So 2 automatic, 10 automatic, and so on. But if a number is automatic in 2 different bases, then it has a lot of structure to it. And this is this famous theorem of Cobham. So which says if a number is automatic in 2 bases, let's say bases 2 and base 10, binary and decimal, then it is ultimately periodic. That sequence has to be ultimately periodic. It can only be a rational number. So I've specialized the theorem. The theorem is more general, but this is a special case of the theorem. Okay. Right. So what are the closure properties of this set? Let's say L is the set of all automatic numbers on base 2. Right. So all numbers of this form, where the sequence n is accepted by some finite automata. So we have just argued that all rational numbers are in this set L. So it's a rich set. Moreover, you can take negations. Okay, so you can just flip the bit, nth bit. That can be done by an automata too. So you can, it's closed under negations. You can, you can say that I can fix some constant and say that these sequences are at most, these numbers are not 0, 1, but between 0 and some constant c, and even then this will be an automatic number. Okay, you can design an automata that will mod out these c's to give a 0 or 1. Interesting property is they're closed under addition. So you can add 2 such automatic numbers and you'll still get an automatic number. Right? And this one is a bit tricky. You can divide by integers, non-zero integers. I'll not go into the proof. This is the proof idea. So what all this implies is that the set of automatic numbers is a rich set. It forms a vector space over the rationals. Right? It has a nice structure to it. Okay. What about multiplication, right? So unfortunately, it's not closed under multiplication. The idea is, if you look at the nth bit of this product of 2 such automatic numbers, it's a convolution of this form of all the n bits of xi and of y, x and y, the first n bits. And to do the sum, you will have to store all these n bits. And unfortunately, with finite memory, you can't do that thing. So you can't compute the product of 2 automatic numbers. What about squaring? Yeah, if you were able to do squaring, if there was an automata that can compute squares, you can do multiplication. So squaring is ruled out too. What about inverses? Yeah, you can't do inverse, because if you are able to do inverse, you could write the square in this form, and so you can't do inverses either. So it's not a field, and so it's only a nice some vector space over the rationals. Okay. So this is the first half of the talk where we have been, this is the automata part of the talk, right? So we have these nice numbers that can be computed by finite automata, right? So the nth bit of a number can be easily computed by in finite amount of time. So now in the next half, what we'll be concerned with is the arithmetic properties of these numbers, right? What are the interesting properties of these numbers? So any questions so far? Okay, so transcendence. Yeah, so this, every time I wrote this word, I had to check my dictionary. Yeah. Okay, this is, I've copied this from an original source, so I hope the person doesn't mind. I'm sure he won't mind. He has attained samadhi, so the soul is free. He won't be turmoiled by the brutality I've done to his poem. Okay. So transcendence, right? So to understand transcendence or transcendental numbers, we have to start with algebraic numbers. Yeah? So what are algebraic numbers? Basically roots of integer polynomials. Right? So examples are all rationals are algebraic numbers. So square roots, any kth radical, they are all algebraic numbers. So numbers which are not algebraic, which are not roots of an integer polynomial, are transcendental numbers, right? And so again, by Cantor's argument, we know that there are uncountably many numbers which are transcendental numbers. However, it took time to actually give a concrete example, and the first concrete example of a transcendental number was by Liouville, and subsequently Hermite and Lindemann showed that E and pi are also transcendental. So what is the most fundamental theorem in this area is this of Diophantine approximation, which is actually maybe not the most fundamental, but one of the most fundamental theorem is this, right? That we cannot approximate algebraic numbers very well by rational numbers. So now on, when I say algebraic, I'll always talk about irrational algebraic numbers, okay? So rational numbers, of course, you can always approximate very well. So you can't approximate an irrational algebraic number by a rational number very well. So what does that mean? If I take any rational number, P over Q, then if I look at this, how well this approximates this algebraic number alpha, then there is a lower bound which you forget this constant which depends upon alpha and epsilon. Then the lower bound is the denominator raised to some exponent, okay, some exponent d alpha plus epsilon. And Liouville showed that d alpha is the degree of your algebraic number. So n, I have forgotten to write it here, it's n. And then this was improved by Thieu to 1 plus half of n, and Siegel improved this to 2 times square root n, this exponent. So the lower bound has come up, and finally the claim to fame was by Roth, and who showed that the exponent is really 2. So any rational number, if you approximate it, the algebraic number, then look at this distance is at least a quadratic factor away in the denominator, right? And this is tight due to Dirichlet, who had showed that there are rational numbers that can in fact approximate your algebraic number or any real number to a factor of square here in the denominator. Okay. However, Liouville has the advantage that this constant is explicit. This helps us as a computer science because it helps us in deriving complexity bounds and so on. The other results, we don't have any explicit constant. In fact, it's a challenging problem to come up with an explicit constant. So how do we use this result to prove transcendence of a number? Right? So here is an exercise. So let's use it to prove transcendence of the Liouville number. Right? The idea is that there are enormous gaps here. They are between the n factorial and n plus 1 factorial. So you must be able to get very good approximations to your number. Right? So the proof is by contradiction. Let's assume that the number is algebraic. Right? So the theorem says, the fundamental theorem says, I'll forget about the constants, that any rational number, P over Q, approximates this number by a factor of 1 upon Q square, right? At least 1 upon Q square. Now let's take this particular rational number. The sum is all factorials, up till all the factorials, up till some number K. If you look at this difference, that difference is the sum of the tail. So all 2 upon n factorial, n is strictly greater than k, and this is upper bounded by roughly, let's say, 2 raised to 1 upon 2 raised to k plus 1 factorial. So this is our upper bound. And what is the lower bound? If you substitute q sub k here in the theorem, you get the lower bound is at least 1 upon 2 raised to 2 times k factorial. And we get a contradiction if k is large enough, because the upper bound, which is 1 upon 2 raised to k plus 1 factorial, will be smaller than the lower bound, which is 1 upon 2 raised to 2 times k factorial. Since k plus 1 factorial, if k is large enough, will dominate 2 times k factorial. Right? So this basically gives a proof that the Liouville numbers are transcendental. Right? Since you are able to get such a good approximation to the number. Right? Now let's take this idea and try to apply it to the Fredholm number. Right? So what is the Fredholm number? Let's recall. So the 2 raised to nth bit is 1. So the nth bit is 1 followed by 0. So any power of 2, you have a 1 there. Okay. So let's try to do the same strategy. So let's assume the number is algebraic. Again, the theorem says any algebraic number, if you take any rational number p over q, then the lower bound is 1 upon q square. Right? Again, there are some gaps, exponential gaps here. So let's take this rational number, pk over qk. So sum over all the bits up till k. So 2 raised to minus 1 upon 2 raised to 2 raised to n. Right? And if you look at the difference again, which is this tail term, this is upper bounded by roughly 1 upon 2 raised to 2k plus 1. And what does the lower bound give us? 1 upon qk square, but 1 upon qk square is roughly the same thing. Right? So 1 upon 2 raised to 2k plus 1. You don't get a contradiction, right? Because upper bound and the lower bound are quite close to each other. unlike the case in the Liouville numbers, right? So, so how do we prove that such a sequence is, such a number is transcendental? So you can try to, go and try to do it in an ad hoc way, and, look at the properties of this number. Suppose it was algebraic, there was some polynomial, and you can try to prove it that way. I'll not do that. What I'll show instead is this very nice result of, use this result of Adamczewski, Bujold, and Luca, which is one of the breakthrough results in this area, which says that we need this notion of a stammering sequence. Okay, so you take an infinite sequence of zeros and ones here. We say it's WC stammering. So W is some constant, some real number which is strictly greater than 1, and C some non-negative real number, okay, or non-zero real number. Sorry, positive real number. So, okay, so we say a sequence is WC stammering if you have two sequences, U sub k and V sub k, which satisfies this property. If you look at the string U sub k followed by V sub k raised to W, okay, so what does that mean? V sub k raised to 1, you repeat V sub k and maybe some portion of V sub k. Even a slightly small portion of V sub k will be enough, since W is strictly greater than 1. So if this string is a prefix of your sequence, and if this ratio of this length of U sub k over V sub k is bounded by some constant, it's not growing unbounded, and the strings V sub k are strictly increasing, then if you have such, if you have such a pair of sequences for certain W and C, then we'll say that this infinite sequence is a WC stammering sequence. Okay? Stammer is because of this strictly greater than 1. Okay, then the main result of Adamczewski, Bujold, and Luca, it's a very nice combinatorial result which says that any infinite sequence which is WC stammering is transcendental. The corresponding number is not algebraic. Okay? That means we are able to, using this property of stammering, you are able to get very good approximations. Okay? The proof is a bit complicated. It doesn't use the theorem that I had shown. It uses a vast generalization of that theorem. It uses the p-adic subspace theorem. Once it has done that abstraction, we only need to check whether for our sequence, infinite sequence, if we can find we can show that it's WC stammering for some constants, W and C, where W is strictly greater than 1. Right? So if you look at our Fredholm number, here is the sequence. So the claim is it's a 2-1, there is a 2-1, it's a 2-1 stammering sequence, at least 2-1 stammering sequence. And here is the sequence, the pair. So you take UK to be the first prefix of length almost up till 2k minus 1. So this is the power of 2's. You have a 1 at all the power of 2's. So UK is the string all the way up till just before this 2 raised to k minus 1. Vk is the subsequent string, which is of length 2 raised to k minus 1 again. So 1 followed by these many zeros. And what do we have? We have this at 2 raised to k, we have 1, and then we have a bunch of, a huge number of zeros again. And that's really Vk repeated up till this point. In fact, it's much, so the power of W here is 2, so Vk is repeated twice. And so UK and followed by Vk square is a prefix. UK by Vk is clearly bounded by 1 here, and Vk is, the length of Vk is strictly increasing. Right? So it's a very simple proof that shows that the corresponding number is transcendental. Okay? So you don't have to do, so they have abstracted out all the algebraic number theory part, and one just has to check this stammering property, okay, which is at least easy to do. Okay? Any questions?
No question at all.
No question. Okay, fine. So, so that was just the basic result. What they really showed, Adamczewski and Bujold in their breakthrough paper, was that all non-periodic or periodic automatic numbers are transcendental, basically using the stammering criteria. Right? And that was not only enough. So, okay, you can't compute algebraic numbers. What does it mean? You can't compute irrational algebraic numbers in finite memory. Right? What about, okay, forget about finite automata. What about pushed-on automata, which are slightly more powerful? You have this memory, but you can access the memory in a last in, first out manner, right? In a stack manner. So, recent result, they showed that even you can't use a deterministic pushed-on automata to generate an automatic, to generate an irrational algebraic number. Okay. So, finite automata are out, deterministic push-down automata are out. So what is the main question here? So where are they leading to? So the goal is this conjecture of Hartman's and Stern's, which says that claim is the nth bit. If you have a Turing machine which takes linear time to output the n bits of a number, then that number cannot be an algebraic number, right? So you can't output the n bits of an algebraic number, the first n bits of an algebraic number in linear amount of time on a Turing machine. This is the Hartman-Stern conjecture. It's still open. What Adamczewski and others have shown that if you had a multi-stack Turing machine, then you can't do this thing. Okay. And why? Why is this hard? So all the current algorithms for computing the n bits of an algebraic number take m of n time, where what is m of n is the complexity of multiplying two n bit numbers, and our current best estimate for m of n is order of n log n. Okay. So we are not able to do this computation in linear amount of time, slightly more than linear we can. Okay. But really the challenge here is, okay, how much time does it take to compute the n bit of an algebraic number? Well, so what I'm assuming here, the conjecture assumes that n is given to you in unary, right? So you can use that much space, n bit space. But what if n is given in binary, which is really the case in practice, right? You are given n in binary and you want the nth bit of your algebraic number, then how much time does it take? Well, somewhere sitting up, it's very, it's high up in the counting hierarchy, right? We don't know of anything which is better than this. So there is a big gap between the lower bound. Lower bound says we can't compute algebraic numbers, the n bit of an algebraic number by push-down automata, and then, well, how much time does it take to compute? Will take somewhere in the counting hierarchy. Okay, so there is a big gap here, and the goal is basically to understand what is the complexity of algebraic numbers, or even special classes of algebraic numbers. Can you compute square roots, for instance, better in faster time? Even that we don't know. Okay. Yeah, so that's basically the reference for this area is Alouche and Shalit, this book. It's a very nice book, and I'd like to end my talk. Yeah, thank you.
Now I'm audible. Yeah. So thank you for the introduction, and thank you for inviting me here. It's always a pleasure to be here in IMSc. I'm sad that I couldn't come for the entire event because I was traveling, so I made it just for the last day. Okay, so my talk is titled, "What is randomness?" So it's best that I start with that question, right? So the question, "What is randomness?" can work on multiple levels. It can work, well, from a purely mathematical level. You could ask what randomness is all about. You can also ask just at the intuitive level. You can also ask this question at like a philosophical level. But here what I really meant, at least with the talk title, was just at the most intuitive level. So we live in a universe. We look around us. There are all kinds of phenomena and well, events happening around us. And some of these events look random. Some of the outcomes just look random to us. And again, when I say look random, I'm just talking about just the English usage, just the common usage of looks random. And one could ask, why is it that some phenomena look random and some others do not? So what's all this about? And you could ask an even more fundamental question, and that is, what does it even mean for something to look random? Right? Now, again, like I said, this can work on like multiple levels, but right now I'm just talking about the most intuitive interpretation of these questions. Now, this also is related to a very big open question, which is there randomness in the universe at all? Like, are there physical sources of randomness in the universe? And this is quite a big open question, and we don't know if there are physical sources of randomness, but if you ask scientists from various areas, they might give you various answers as what might be candidate sources of randomness. So I've listed some of these, like Brownian motion, atom decay, radio noise, sunspots, stock markets and stuff. Now the first two are kind of like verified sources, not of randomness, but I'm saying that I asked somebody who I trust. So the first one is Brownian motion was, I basically asked a friend who works in biomimetics, and he told me this is the first candidate source of randomness that comes to mind for him. That's what I put. Atom decay, I asked a physicist who works in AMO physics. And she told me, well, this seems to be the first thing that I get in my mind. And the remaining are from Google, so I don't know what they're all about. Okay, so these are like some candidate sources of randomness, and many of these are, like I said, I asked people in like computational biology or biomimetics and physics and stuff, but I am a computer scientist. I'm no physicist, okay? So the quintessential example event or example random event for computer scientists is the coin toss, okay? And we define it theoretically, at least in theoretical computer science, in all our courses, we define the coin toss as a random source. And the way we do it is the following. It's defined like this. It's an event with two outcomes. You either have heads as an outcome or you have tails, and they're mutually exclusive, and we define it to be a 50% chance for each. Okay? And well, in theory, this is a source of randomness simply because it's by definition random. You've got a 50% chance of getting heads or tails, yeah? And in almost every course that we do in theoretical computer science, this is like the quintessential example. But turns out the coin toss is also used as a source of randomness in several casual real-world events, okay? Like, look at these guys, right? They're using a coin toss. The one in blue is our main man. So he's going to toss a coin, and the other person has to call it. Yeah? So that's the random event that is used before a lot of sports events, including cricket, as is the case over here. Now, so the way it's defined in practice is the following, right? So this part is how it's done. Someone tosses a coin, and you're supposed to call heads or tails. And that's a prediction. Okay? So that's the only difference. You cannot just define it to be random in practice, and you've got this call, which is a separate thing. So now I'll recall that in English, the opposite of the word random is predictable. Okay? So the calling heads or tails is essentially that prediction that you're asking. So now you could ask, what's really random about this practical coin toss that we do before a cricket match, right? So here are two thought experiments. So the first one is the following. Imagine you had a machine that could toss a coin almost identically every time. You put the coin into a slot, it tosses it identically, yeah? Then the outcomes are going to be identical. You're always going to get heads, or you're always going to get tails. And that won't look random to us anymore. Yeah? Again, by looks random, I just mean the most intuitive sense. If all the outcomes are just the same, that doesn't look random. Yeah? Here's another thought experiment, which is, imagine you had a really powerful computer, which has several cameras and stuff focused on the person tossing the coin. And it has all kinds of modern technology built into the camera as well as the computer. So you've got all these convolution neural networks and deep learning and AI and stuff, right? And ray tracing and any other buzzword you can think of. So no expense has been spared in creating this computer, and no buzzwords either. And this thing can perfectly predict the coin toss as soon as it sees a person tossing the coin, right? And imagine you have it with you. And now, as soon as someone tosses the coin, as soon as the coin leaves the hand, it tells you it's going to be heads, or it's going to be tails. Yeah. And, so the prediction is being done by this super powerful computer, and will that look random anymore? I don't know. Like if you can immediately tell the answer, it doesn't look random, right? So here's what has happened. We took like a coin toss, which is in fact used in like several occasions as a source of randomness. And in both these thought experiments, so in the first one, we made the prediction itself trivial because the outcomes are going to be identical. So the prediction is trivial. In the second one, the prediction is not trivial because it could be heads or tails, but we have extra computational power, which is somehow able to tell us what it's going to be. So in like the second thought experiment, if you had to call it, you're always going to be right. Yeah, so the prediction is, you're able to compute it. So there seems to be some connection between able to compute the outcome of an event and the event looking random to us. Yeah, so what is this connection, right? Could it be that our inability to compute is masquerading as randomness? Or is there something more to randomness, right? So if it is true that our inability to compute the outcome is nothing but randomness, and then there is no randomness in the universe at all, right? And that's a possibility. Maybe the universe is just deterministic. That would be very boring because everything is predetermined. Nothing happens by chance, and there's no such thing as serendipity, right? It's all just boring. So I hope that's not the case. And one could ask, is there more to randomness than just this, right? So with that being said, that was kind of like the motivation for this talk. What I'm going to do is introduce a very fascinating area of mathematics called pseudo-randomness. And the plan is to cover two ideas from like classic results of pseudo-randomness, nothing about the state of the art. The state of the art is fairly sophisticated. And so the plan is just like two very elegant ideas from back like 80s and 90s, okay? So before I go ahead to like the technical part, one disclaimer, I do not work in this area, so I'm not really an expert. But feel free to ask me anything you want over coffee, and we can look it up, and I'll learn something as well. Okay, hopefully I've not lost anyone already. The losing part happens now, okay? At least in my opinion, there are like two main lines of research in pseudo-randomness. The first one is hardness versus randomness, which I'll tell you about. And the other one is assuming you have true random sources, how powerful is randomness to computation? Like, can we trade some memory space and get rid of randomness, or like get rid of the need for randomness? Or can we trade randomness for running time? Yeah. So, okay. So before showing you like the first paper, whose idea I want to present, I would like to make one thing formal, and that is what does it mean for something to look random? Okay. So as is the case in mathematics, we have to formalize everything and make everything precise. Okay. So here's a definition. So imagine you've got a randomized algorithm, and in the context of everything I said so far, your randomized algorithm is like an observer, okay? And it uses some R bits of randomness, yeah, for some n bit input. And you've got a function g. Again, so to put things into context, g is like some event that A is able to observe, okay? And what this says is that the output of G looks random to this algorithm if the way the algorithm behaves when it's given the output of G versus the way it behaves when it's given independent random bits is very close together. Yeah? So let me just go through this line over here. I should have probably mentioned that the randomized algorithm only outputs yes or no. Okay, it's just a 0-1 output. It's not computing some number. So the first quantity is what's the probability that the algorithm outputs 1 when given R independent random bits from like a pure random source. Okay, and the second one is you're going to take only L independent random bits and you look at the output of G on these L bits. Okay, and you feed that to the algorithm A. If the algorithm behaves very similarly on both these, then it seems natural to say that, well, the output of G looks random for A. Okay, epsilon is like some small number. Yeah. So here's an example. So suppose G was just the identity map, right? Then it takes L many independent random bits and just outputs the same L bits. In which case, of course, the algorithm behaves the same on G as well as on independent random bits because it's the same thing. Yeah. So things get interesting when L is less than R. Okay. So So if L is less than R, then what happens is that you're giving few independent random bits to G and outputs a much longer string. Yeah. So the amount of randomness in the output string is really only L bits, but the algorithm doesn't really see such a big difference in the output of G versus getting completely independent random bits. Yeah. So this is a fairly natural way of formalizing what it means to look random, right? We're basically saying that the algorithm behaves very similarly whether it looks at G or whether it looks at independent random bits. Yeah. So when L is less than R, G is called a pseudo-random generator, and L is its seed length. Essentially, since we're picking an input to G independently, well, uniformly at random, then so that's like the random seed for it, and it stretches the string to a much longer string. Okay. Okay. So the first paper that I wanted to tell you about is this paper simply called Hardness versus Randomness, and this is quite an old paper. It's actually from '88 or '89, at least the conference version is, and this is the journal version from '93. So I'll just read through this. It kind of fits in very well with everything I was saying so far. So it says we present a simple new construction of pseudo-random bit generator. I'll tell you about this soon. Stuff and 1 sec, it stretches. Right, so they say it stretches a short string of truly random bits into a long string that looks random to any algorithm from a complexity class C. And this is the most important part, using an arbitrary function that is hard for C. So here's what's happening. Imagine you've got a machine, right? And this machine cannot compute some function f. Yeah? What they're doing in the paper is, they're like, well, this function cannot be computed by this algorithm or this machine that you have. We will use this function to come up with a sequence of bits that will look random for this machine. Okay? So it's very much like what I was talking about earlier, is our inability to compute something the same as looking random. Yeah? So over here, I should make like one thing precise. So what do they mean by an arbitrary function is hard for C? So it's a bit different from the usual notion. So we say a function f is hard for some computation model C if it cannot even be approximated well by machines in that computation model. So imagine you have like polynomial time machines, polynomial running time machines. Then if you take a function that they cannot even compute in the average case, as in they cannot even approximate it well, then you call that function hard for that. Okay? And what the paper does is they take such a function and show that you can now create a pseudo-random generator using this function. Yeah. Okay, so I just want to tell you about like the main idea of this thing. And the way it works is the following. So take a function that this machine cannot even compute. Well, cannot compute even even in the average case. Yeah, cannot even approximate the function. So here's like a very simple way to do like a 1-bit stretch pseudo-random generator. You pick x1 to xn uniformly at random and independently at random. So these are pure random bits. And you simply compute the function f on these bits. Okay? And you attach this output at the end of these n bits. Yeah. Now, well, intuitively, the first n bits are anyway random. We pick them independently at random. So of course, the first n bits look random for the function, for the machine. And the last function, we just, the last bit, we assume that this function is hard for the machine. Yeah. So of course, even the last bit will look random. Okay. That's just the intuitive thing. So this is a 1-bit stretch, by which I mean we used n bits of independent randomness, and we added one more bit to it in a way that the resulting sequence still looks random. Okay. So what they do in the paper is much better, and that's the core idea of the paper. They do a much better stretch, and the idea is the following. You take a slightly longer string, independently at random, each bit, and you construct a family of subsets, each of size n, and with small pairwise intersection.
So is the claim that if x1, xn are independently chosen,
Yeah,
and if you apply a hard function f,
yeah, at the end, yeah.
the length of string of length n plus 1 is also, is that here?
Yes, it will look random for the machine M. Yeah, that's right.
But if you have a definition of a hard function,
Yeah,
you have a definition of an identical.
right, right.
So is that a theorem that if f is hard, then this is whatever?
Yeah, so if f is hard,
You said looks random.
it looks random to the machine M. Yeah. So what I mean is that M will behave, so I mean in this sense. So M will behave almost as if it got n plus 1 independent random bits, which just maybe like an epsilon, like just a small difference in behavior, that's it. Exactly, yeah, it will fool it, yeah. So in fact, like since you brought up that point, so in this definition itself, there is some insight that we get into all of this stuff, which is, so look at this sentence. It says, intuitively, the output of G looks random to A, and the insight there is that what looks random is a function of the observer as well. Okay? So like a function might look random for one machine, but it might not look random for another machine. And just in making the term looks random precise, there is some insight that we get out of that. Okay. Okay. So going back, yeah. So just to repeat, this string of n plus 1 bits will look random for this machine M, because we assume that f itself is hard, and this can be proven. It's fairly easy to prove this. So what they do is the following: you take a slightly longer seed, okay, and then you construct a family of subsets of size n with small pairwise intersection. I'll make it precise. And then you apply f to the projection of the seed that you took to each of these subsets. So let me make this precise. So you take a family of subsets. We've got m of them of this universe, 1 to L. And we call this a Kn design if each subset has size n and the intersection is at most k. The pairwise intersections are at most k. Okay? And the main idea is the following. You construct such a family of subsets, which is a Kn design, and you choose a seed at random. So you've got x1, x2, xl. You've chosen L bits at random. And the pseudorandom generator is now the following. You apply f to the projection of x on the first subset, and apply f to the projection of x on the second subset, ... Okay? So once again, each subset has exactly n positions. And when you take projection, what I mean is you've got this long string and you look at the bits present in the indices of S1. That would be the projection of the vector x onto S1. Yeah. So you do this and they show that in fact G will fool the machine M with like carefully chosen parameters. Okay. So I think I've written some parameters over here, even though I do not want to go into it. So they construct log Rn design. So I'm not going to prove it, but let me just tell you like why this should work intuitively, right? So imagine you had k equals 0, right? Then you've got a family of disjoint subsets. Yeah. That means that you've got this f is being applied to independently chosen random bits, and the applications of f across them are completely independent. Yeah, like the input sets are completely independently chosen. So of course that's going to look random, right? Not of course, but intuitively. Yeah. Now what's happening is that we're going to allow for some intersection among the subsets. So now what happens is that you can have many more subsets because you're allowing for some small intersection, but because the intersection is going to be something like log r, or like log of, yeah. So I'll not get into the parameters, but the intersection is going to be so small that there's still a lot of independence among the subsets. Okay, so that when you actually apply f on all of this, it still looks random to the machine M. Okay, so so they actually give a construction of these families of subsets, and such intersecting families of subsets are an object of interest in combinatorics. In fact, there's the entire pages of this stuff. So you can look at, for instance, Peter Frankel's publication list. I think he's on like 90% of these intersection family constructions. He's an author on them. Okay, okay, so that was about this paper, and I think it's like a very elegant thing, because you start off with trying to fool a machine, and you make it into some kind of combinatorial object, and that's all you want to do. Just want to construct this family of subsets. And this is called the Nissan-Wigderson design. It's used even in the state of the art. A lot of the modern constructions are based off of this, or inspired from this, basically. It's just that things get a bit more sophisticated in terms of construction, so that you can get better parameters. Okay, okay. So that was like one idea. The other idea was this one, which has to do with can we trade memory space for randomness? Okay, so the title is Pseudo-Random Generators for Space-Bounded Computation. And so let me just go through this. So they construct pseudo-random generators which try to fool algorithms which use only space S. Okay? So imagine you've got a space-bounded machine. You can only use space S with that. And they convert S log R many truly random bits to R bits. Okay? So the algorithm basically uses R bits, or requires R bits of randomness, and they're able to do S log R. In particular, if you put S equals log n, and R also as like n, then you get log squared n truly random bits to n bits. Okay? So that's what happens over here. Okay, so this is, the idea behind this is slightly more involved in terms of notation than the previous result that I showed you. And we just need one definition really, and we need definition of a hash function. So here's the definition. So a family H of hash functions, of functions H, is called a pairwise independent hash family. If the following happens, you take any two different strings, x1 and x2, and any two strings y1, y2 from the range. Okay, the probability. So the idea is that you basically pick a hash function from this family at random. You're not picking a string at random. You're going to pick a function at random from this family of functions. And the probability that the function on the first string gives you y1, and the function evaluates to y2 on the second string is 1 by 2 power 2m. But let me give you just like an intuitive description of what's going on. So using such a hash family is kind of like a shortcut to picking a string uniformly from the range. I'll tell you what I mean. So imagine you pick two strings from the range. Let's call them Z1, Z2. What is the probability that Z1 equals Y1 and Z2 equals Y2? That's exactly this. Yeah? The probability that Z1 equals Y1 is 1 by 2 to the m, and the probability that Z2 equals Y2 will be 1 by 2 to the m, and the probability that both of them happen is just the product of these two probabilities. So picking a hash function from this family is like picking two independent strings from the range. It's kind of a shortcut, but what really helps us is that they're functions. Okay, so yeah, so the probability is over a hash function that we are picking. So we have a family of functions that we construct beforehand, and then the idea is that you basically pick one function at random from this family of functions, and then we said this should happen for all x1, x2, and y1, y2. Yeah. Okay, and now this is, so let's just start at like level 0, is like what I call it. So assume you've got a hash family from k bits to k bits. Okay. So once again, this is like a combinatorial object that we know several constructions of, and people work on getting better constructions. And the idea is this, it is a level 0 idea. You choose x1 at random, okay, and then, so x1 is a string of k bits. You choose a hash function at random, and then the output or the sort of random string is going to be x1 concatenated with h applied to x1. Okay. So we started with, so I think I've got a calculation over here as well. So in picking the first string, we're using like k many independent random bits. And just trust me that we know hash families with like linear space descriptions. Okay. So in other words, we can choose a hash function also with order k bits of randomness. Okay. That means that we basically chose 2k bits of independent randomness, yeah, and we output a string of also size 2k. Yeah. So it feels like we could have just chosen a new string x2 at random and just output x1, x2. Yeah. But the main idea of the paper is that you can use a certain recursion to do much better. So in other words, this idea basically scales very well. Let me show you. So in level 1, what happens is we pick one string of length k, and we pick only 2 hash functions. Okay? And the string that we're going to construct is, you have x, which we picked uniformly at random. You apply the first hash function to x. You apply the second one. And the main trick now is that you apply this composition of the functions. So you go h1 of h2 of x. Okay? Now, why should this look random? Or why should this be able to fool a machine? That's what they prove. Okay? So continuing, so in level 2, for instance, we'll pick one string uniformly at random from this and 3 hash functions. And we'll end up getting a string of size 8 using this. Because what we're going to do is we'll go x, and we'll of course compute h1, h2, h3 on this. You also have the composition, so I've not put the parentheses because it gets quite ugly. So h1, h2, which is h1 of h2 of x. We also compute h1 of h3 of x, h2 of h3 of x, and h1 of h2 of h3 of x. Okay? So the idea is that this whole thing scales extremely well, and in general, if you want a string of length 2 power s, you only pick s many hash functions. And then you do this idea, right? So if you just do like a very simple calculation, well, we pick one string of k bits at random, and you pick s many hash functions, each of which requires k bits at random. So in the end, we've got sk plus k, right? So that's like k times s plus 1, many uniformly random bits that we used. And our output string is going to be of size 2 to the power s. Yeah. So in particular, if you choose the parameters correctly, you can stretch log squared r, many random bits, to a pseudo-random string of r bits, which will fool any machine which uses r bits and small space, so log space machines. Yeah. So the way I described it is actually, I basically unfolded a recursion. So the way this is defined in the paper is very elegant. Just these 2 lines is the definition of the pseudo-random generator. You have a base level of the recursion, which I was calling level 0. G0 of x is just x. And then, this should be gk, the subscript to g. Yeah? The kth level is simply the concatenation of the k minus 1th level function applied to x and the first k minus 1 hash functions. And you concatenate it with the kth hash function applied on x and h1 to hk minus 1. So if you just unfold it, you get something like this. So the first level, you get just x and h1 of x. And the second level, like I was describing, you get x, h1, h2, and then h1 of h2. Okay? How many minutes?
2-3 minutes.
Perfect, I'm done almost. So one of the most important consequences of this paper is that if you have a randomized machine that uses only log n space, then you can simulate it with a deterministic machine that uses log squared n space. So we basically traded quadratic space, and we've completely gotten rid of randomness in this case. Okay? The state of the art over here is, instead of 2, you've got 1.5. Okay? And it's strongly believed that randomness doesn't help with computation when it comes to log space machines. In other words, one of the biggest open problems and something that still people are working very actively on is to make this just log n, and hence showing that randomness is useless when it comes to log space computation. So in conclusion, and I'm well within time, what looks random is a function of the observer, and that came straight from the definition at least. And it seems to be so in like the way, at least in theoretical computer science, this is very true. And hardness of a function can be used to fool the machines for which it is hard. So this kind of like the general theme that I was talking about earlier, where I was asking, is it true that not being able to compute something is nothing but randomness? At least in theory CS, it seems to be the case. At least there's a lot of evidence for it, although we haven't proved it in the general case. The last point I didn't talk about at all, but this is actually a follow-up paper by Impagliasso and Vigderson. I'll be happy to chat about this over coffee, so you can just ask me about it. Yeah. Okay, thank you. Thank you. No, sure, yeah. Thanks so much. He wants us to look there. Never mind.
Before we end the session, there's a small announcement. As you know, we released day before yesterday the My stamp and the envelope commemorating the 60th year. Okay, so we are putting here this for display so that all of you can have a look at it. Okay, thank you very much. We'll be back at 11:30.
Okay, welcome back everybody. Let's get started with this session. There are 6 talks in this session, each 15 minutes. So we'll try to be on time as much as we can. And first we have Shivam Gola. He's going to be talking about dark matter from particle physics perspective.
Shall I start? Okay. Hello everyone. So I will talk on this dark matter from particle physics perspective. So before I begin with, I want to talk on 2 things because it will be very quick. So what is dark matter? First thing. So one line definition to dark matter is that it is not made of proton, which makes up everything we know. And second thing, it does not interact with light. That's why probably it's called dark matter. And we want to study dark matter from the particle physics perspective. There could be other ways like cosmology or astrophysics, but those things I cannot talk. So yeah, so I will talk on that. So my talk is divided in 2 parts. So first part is the pedagogical introduction. And introduction part we may ask these kind of questions: what is dark matter, what is not dark matter, how to detect for it, and why we believe on it. So these kind of things we will talk on. And second part of talk is little more technical, which is basically one of my work. So I will describe that. So first question is why we believe dark matter. So basically what are the reason behind we see. So there are, I listed 5 of them. First is rotation curve, second is lensing, third is bullet cluster, fourth is CMB, and fifth is cosmological simulation. These all physics are at very different scales. Galaxy has some scale means size, and clusters has very different scale, and CMB is like universe size scale things. But the point is, in each scale, we are seeing some anomalies, which is not described by the theories. Theory means Newton's laws. Okay, so solution to these problems, all these observations, is that either theory has some problem, or either there is some extra matter, some extra stuff is there, which is not like regular matter. Regular matter means made of protons, atoms, or molecules. Those things are not there. So we will go with the second possibility, that there is a extra matter which is required to solve all these problems. There are many evidences, but I just listed 5 of them. So one thing is sure that there is a dark matter. Now, if we know there is a dark matter, what it is. So right side there you see there is a pic, which is basically the standard model of cosmology, which says that there is 5% ordinary matter, mean atoms, molecules, stars, planets, and 25%, which is like 21 here in the pic, is dark matter, which we don't know. It is completely unknown, and the rest is also unknown, which I will not talk on. So there are some properties or some features of dark matter we know. And what are these features? The first thing is it does not interact with light, as I saw. That is why it is not been seen yet. Second thing, it is stable. Stable means it has a lifetime which is infinite, or it has a lifetime which is very large. That is why we are still seeing it today. Okay. Third thing, it is cold. Cold means it moves very slowly. Slowly means compare it to speed of light. So okay, so it moves something like speed of planes, airplanes. Okay, so that is what cold means. Third observation is the today's number density. Number density means what is the amount of dark matter today exists in the universe, which is 25%, and mathematically we can write it like this: omega dmh square 0.12, and there could be many others, but these 4 are very strong. Then question is, we identify there is a dark matter, and what are the features of it. So next question is, can we should identify. Okay, so first proposal was that MACOs, it stands for Massive Astronomical Compact Halo Objects, and these are actually group of objects called neutron star, dwarf planets, death star, black holes, and collectively people have there are 2 collaborations called MACOs and Anomalous. These people have looked up dark matter, looked up these these objects, and they did not find it. So the point is, dark matter is not MACOs clearly. The second thing, if dark matter is not these extended objects, these very large objects, then it should be something we look up in the fundamental particles, atoms, molecule, or nucleus, or maybe beyond that. So so beyond that, physics is described by a standard model of particle physics. Okay. So in the right side, you see K pix, which is basically the all the non-fundamental particles that describe the nature. And the point is, none of the particles satisfy the dark matter features. So it should be electrically neutral, it should be stable, and it should be cold. So none of the particles that satisfy, none of the standard model particles satisfy those features. So standard model has no dark matter candidate. So if dark matter is not in the standard model, not in the cosmology, mean dark matter, black holes, neutron star, those things are not dark matter, then what it is? So that we will ask, and this thing leads to something called beyond standard model of physics. Okay, so we will come to it again, and so we had then one last point, how to search for it. So there are three main ideas that has been followed up. It's called direct detection, indirect detection, and collider searches. So what happens in collider searches? Two high energy proton beams collide, and it may happen that dark matter could be produced, and that will be like a missing energy signals that can be seen in the collider experiment. The second experiment called direct detection. What happens in direct detection, that dark matter interact with the protons or detector nuclei, and it may scatter, and it can induce some energy change that can be measured. So that is called direct detection. And third method is an assumption that dark matter have some anti-dark matter, or dark matter may decay, but with very less probability, and it can give you some non-particle like photons or neutrinos that can be detected. So this is the third method of detecting it. And so we will talk on what is dark matter, what is not dark matter. Now, how to study dark matter? So we should start from the standard model, and a standard model has no particle. So we must go BSM, okay, beyond the standard model physics. So starting with BSM, we should add a particle which represent a dark matter. Representing means it should be electrically neutral, it should be stable, and it should produce the right relic density, and then it should explain this constant like relic density, direct detection, indirect detection experiments. Okay, sorry. So yeah, so one should make a model like that. Okay, and then I move to the part 2. So part 2, this is a model. Okay, so this is one way of looking at it. You see some of the particle on the right side, Q, U, D, N, these are the particles, and there is some extra particle, and chi in the last is the dark matter candidate in my model. Okay, and there is some symmetry group which is basically telling that these particles have some properties. These 1, 2, 3 numbers, these are just telling that these Q, U, D, all these particles having some properties, some features. Okay, and another way of looking that same model in this way, sorry. Yeah, so this is one way of looking at the model. This is another way, writing all the mathematical stuff, allowed terms, and we can compute from these mathematical terms what is called lifetime, decay bits, and probability of some process happening. These things we can calculate from the model. Okay, so first check. So we have wrote a model where dark matter is there. We have added, and so first check we need to see that whether it has no electric charge. First check is already done by the construction. Second thing, we should look for whether it is stable or not. So that is what done is in this plot. There is a colored region you see, and there is a white portion you see. So colored region basically says that basically the disallowed region from theories and experiments on observation or from the model. The white portion is where the model says that there is certain parameter space which is allowed. So basically this comes from the lifetime bound. So what model telling that dark matter is in this white portion is allowed by the lifetime constant. So this is done for certain benchmark which you see, and we can do this analysis again for. So this is U1 model, and I chosen a very generic U1 model. Okay, so generic U1 model mean you can go. There are many types of U1 model, and you can shift to one U1 model to another U1 model just by choosing the right parameter. Okay, so that is what done here, and each U1 model you see some white portion and some colored region. So white portion is the one where the lifetime constant is satisfied. So it's saying that first check is done. Our model has a viable parameter space which satisfies the second property, second requirement of dark matter, that it should be stable. third thing we should look for after checking that it is electrically neutral, which is by construction in the model. Second thing we should look for the lifetime. Third thing we want to see the relic density, which is mean currently or today the energy density of dark matter today, which is like 25% or 0.12 in mathematical. So these are the results, and you see some colored portion and some colored curves. So colored curves basically represent the relic density behavior. Relic mean energy density behavior, and colored portions are the constants. Okay, so all those colored portions are disallowed region, and the curves which is in the white portion, which is actually allowed. So what it's saying that relic density or the energy density, which is 25%, is satisfied on these color curves when it is in white portion. Okay, so this is done for certain benchmark, certain free parameters of the model, and we did the same analysis for more U1 models. Okay, and you see the more or less same behavior. There is certain white space where you see red and orange curve, which satisfy exactly the relic density thing. Relic density means total energy density. So yeah, so this is done for many U1 models. And then we have seen the relic density. Next thing we should look for whether model has a feasible parameter space which is allowed by the direct detection bound. So this is what is done here. So you see again the colored region, which is again something called like background things. Okay, so our signal, direct detection means you are looking for the particles. Okay, so looking for particle means you are looking for the right signal. Okay, so that signal should be above the background, and the orange region is actually the background. Okay, and you see something called a xenon 110 LZ. These are experimental bounds. These are experimental bounds. So, and you see the red and pink curves. Those are the model predictions. Okay, so you see if your model's prediction lie above the background and below the constraint experiment, it has certain feasible parameter space. So mean it is passing the test of the registration. So this is one way. We have done this for other neutrino background as well. And yeah, so in each plot there is small parameter space which is allowed by the bounds. So that these are auxiliary results, and I think these are not required, but these are okay. Yeah, that's all.
Thank you for finishing on time. So, okay, next we have Suprabh. He is from IMSc, of course. And he'll be telling us about sterile neutrino searches with a duty-rated liquid scintillator. So 15 minutes? Yeah. I'll give you like 2-3 minute one. Okay.
Okay, so hello everyone. The topic of this talk is sterile neutrino searches with a deuterated liquid scintillator. This is the outline of my talk. So I'll basically start with introducing, very briefly telling you about what the short baseline anomalies are and why they hint towards the existence of sterile neutrinos. Then I'll talk about what two-flavor neutrino oscillation probabilities are. After that, I'll talk about deuterated liquid scintillator and what kind of sterile neutrino sensitivities are possible with them. And finally, I'll conclude with the challenges that we're facing with estimating the background events. Okay. So, so for people who don't know what neutrino oscillations are, so neutrinos may start as some flavor, and when they propagate over a certain distance, if you detect them, the flavor changes basically. So a neutrino which was produced as a nu E can later be detected as a nu mu or a nu tau. So that's a very simple description of neutrino oscillations. The typical neutrino oscillations that we observe require two mass square differences, which essentially explain as the solar oscillation anomaly and the atmospheric neutrino oscillation anomalies. And the mass square differences that we require for explaining those anomalies do not fit with some of the anomalous results that we are observing at certain other baselines. So in other words, the baselines, which is the distance between the source and the neutrino detector, for these experiments is too small to let neutrino have enough propagation time or distance in order to evolve into certain other flavors. So what are these anomalies? So you have, to begin with, a new mu flavor, and you have a certain expectation of the backgrounds, which are shown by these green and the red patches. And then you observe, when you look for the new E driven events, you're seeing a lot of excess. So here, basically, this blue patch shows you the best fit with the, if you consider that there is neutrino oscillations happening between the new mu and the new E flavor. So this was one experiment which ran in nearly around 2000, and later to check those results, another experiment was planned in the US, and it also is observing similar events where you have a new mu or a new mu bar to begin with. So you should not expect any electron-like events in the detector, not above the expected backgrounds. But what you observe is that you have a lot of anomalous excess of electron-like events. So yeah, there's this another baseline. There's this another anomaly which I'm going to talk more about. So basically, what you have is that you have new, as you all know, in nuclear reactors we have new bars coming out, and so if those new bars propagate for substantial distance, then they may oscillate into other flavors, which is to say that the probability that the new E remains as a new E may start deviating from 1. And in the standard neutrino oscillation scenario, we expect that to happen only when the neutrinos have traveled roughly around 1 kilometer. So if you see this 3 neutrino curve, which represents the standard model of neutrinos, the oscillation or the P nu E to nu E will start deviating from 1 only after they have reached 1 kilometer. But if we have additional sterile neutrino, then those oscillations can actually kick in at very shorter distances of the order of 10 meters away from the reactor core itself. Okay, so this is the neutrino anomaly, and so the most economical way of explaining these anomalies is to just add another another species of sterile neutrino. And since we know that the standard model can only accommodate 3 electroweak neutrinos, so this additional neutrino must be a standard model singlet. So yeah, so conventionally we call these neutrinos as sterile neutrinos, and so sterile neutrinos cannot be detected through any of the particle physics interaction, and the gravitation is also, their masses are also too small to have any kind of gravitational effect. The only way to sort of observe this is indirectly via mixing with active neutrinos. So we just call this model as 3+1. And in order to explain the previous anomalies, you require the neutrino masses, the mass of the heavier sterile neutrino to be around 1 eV. Just for a reference, the current constraint on the lighter neutrino masses is of the order of 1 over 100 EVs, roughly from the Planck data. So this is 100 times larger. Okay, so this is a simple expression for neutrino probabilities in 2 flavor, which is what we are concerned with for any result that I show in here. So basically, there are only 1 mass square difference, or only 2 mass eigenstates that we need to worry about. So it's a very simple expression where you have a new alpha being E mu or tau to start with, and when it propagates over time, you have a simple Schrödinger-like wave equation time evolution for that, and then you later just superimpose with the final flavor that you see. And in a 2 flavors scenario, that expression is simply this, where a new E where a neutrino which is born as a new E can later be detected as a new E with this probability, and it may oscillate to something else with this probability, and you can see that the sum of these 2 probabilities is just 1. So here we have sensitivity to only 2 oscillation parameters. One of that is the effective mixing angle, which is the mixing between the mass eigenstates and the flavor eigenstates. And there is only 1 delta m square we need to worry about, which is the mass square difference between the heavier eigenstate, the sterile neutrino, and the lighter ones. So this table here roughly gives you the kind of mass squared sensitivity that we have with the reactor baselines and energies. So these are the ones that we are concerned with. If you are at 1 kilometer, you will be sensitive to the solar, the atmospheric scale. If you're at 100 kilometers, you'll be sensitive to that solar scale. At very short distances, we may have sensitivity to 1 over 10 or roughly 1 eV square mass square difference. Okay, so our focus is to see what a deuterated liquid scintillator can tell us about the sterile neutrino searches with a with a reactor neutrino source. So as an example, we consider this reactor experiment, which is a reactor nuclear power plant, which is situated in Kudankulam in Tamil Nadu. And the power of each unit is 3 gigawatt thermal. Here I have shown the neutrino fluxes that come out from the nuclear power plant. Here you have the 4 isotopes. And typically these isotope fuel composition evolves with time, but this is the typical ratio that we have. So you can see that the fluxes are exponentially falling with time. And yeah. So why a deuterated liquid scintillator? So one of the main reasons to use a deuterated liquid scintillator instead of a typical liquid scintillator that the neutrino experiments employ is that it has sensitivity to both the charge current and the neutral current events. And India is one of the largest producers of heavy water, so having a deuterated liquid scintillator is not a very difficult job for us. And so the pluses in this setup is that the neutral current events can provide additional sensitivity to the sterile neutrino oscillation parameters, and which is not possible only with charge current events. But as we see, it comes with its own set of challenges, especially with respect to background events. And just to give you a perspective, it was because of observing the neutral current events that Snow experiment could conclusively establish that neutrino oscillations, neutrinos are actually, the total number of neutrinos is conserved, and it's just that they are oscillating from one flavor to another, for which the Nobel Prize was awarded in 2015. So these are the cross sections for deuterium. So here I have the total cross section as a function of the neutrino energy, and this is shown for both the charge current interaction and the neutral current interaction. And if you compare this cross section plot with the previous exponential falling flux plot, if we just simply multiply them, assuming that none of the neutrinos are oscillating, then you would see that the typical peak that would happen is around 4 or 5 MeV. So that's that's in the that's when neutrinos are the particles which are being detected, which is not possible. So instead, what you see is the visible energy, which in the case of charge current events is a positron, and in the case of neutral current events is a proton. So in the case, so these are the typical differential cross sections. So some of the energy is taken up in order to dissociate the deuterium, and then later and most of the neutrinos in the case, most of the positrons in the case of charge current then would peak at roughly around 4 MeV for a 8 MeV true neutrino. And then, so this is the profile for charge current. In the case of neutral current, it's different because the daughter neutrino particle takes away most of the energy, and the remaining energy is distributed between the proton and the neutron, and they typically peak at very small energies, roughly around 200 keV. Yeah, so these are the charge current interactions. In the case of, so these are the neutrino interactions. In the case of charge current, you would have a nu bar which hits a deuterium, and then you have a E plus, a positron, and 2 neutrons in the final state. The positron would give a Cherenkov light signal, and these 2 neutrons then act as a tag. So you observe 2 gamma ray lights. So this is a very clean signal. So you have a prompt and then 2 delayed events. In the case of neutral current, this nu bar would just dissociate. So you have a nu bar which takes away most of the energy. You would get you would get the scintillation light due to the protons, and then this neutron can as a tag, acts as a tag for the neutral current interactions. If you did not have deuterium, in other words, if you don't have this neutron, then you don't get this tag, and it's very difficult to observe this interaction without a deuterated liquid scintillator. Okay, so these are what the probability plots look in the case of the baselines and the energies that we are concerned with. So in the red curve shows you the disappearance probability where a nu E is oscillating to a nu E, and the total flavor. So this essentially represents the probabilities that a nu E could oscillate to a nu E or a nu M or a nu tau. In the case of 4 flavor, and in the case, the black line represents the nu E, the electron disappearance probability in the case of 4 flavor. So this essentially, so if you see this equation here, this is essentially 1 minus the probability that nu E's are oscillating to some sterile flavor which we cannot observe. And if there is no sterile neutrino, then this sum is going to be equal to 1, which is the case for 3 flavor. In the case of 4 flavors, then this again is essentially equal to PEE, because we are in a two-flavor assumption where PE mu and E tau are very small. So I mean that is visible, that is clear with this through this feature here, where the red line and the there's essentially no difference between the red and the blue curves. So some of the few good things about this channel is that this does not have sensitivity to the matter effects or the mass ordering or octant or CP violation. So any deviation from that, what you see from the expected, can cleanly be attributed to either an effective mixing angle with the sterile sector or a mass and a mass square difference. Okay, so here I'm showing some events plot. So these are the total number of events as a function of the visible energy. For the kind of power that we have with the nuclear setup, the nuclear power plant, we expect roughly 500,000 events for the neutral current and 300,000 events for the charge current. The neutral currents even essentially peak up at this very small baseline, very small energies, and the charge current more they are spread out up to around 5 MeV. And here on the these plots below, I'm showing the ratio of the oscillated over unoscillated event rates. So any deviation from one signals an oscillation kind of feature, and you can see that for a 30-meter baseline, both with very small values of the mixing angles, 5 degrees and 10 degrees, you'd see oscillation features due to both mixing angles as well as mass square differences in both the charge current as well as the neutral current channel. So modulo any of the uncertainties in the flux normalization, the cross sections, etc., the physics itself is sensitive to the oscillations in both the channels, charge current and neutral current. So yeah, okay. So these are the final sensitivity plots. So for comparison, I've shown the Dirac excluded region in the delta m square 4 1 sine square 2 theta 1 4 plane. What is on the left is the region that is, sorry, this is wrong. So yeah, so what is on the right is the region that is excluded, and this whole region is allowed. So so you can see that even with much lesser statistics, the results are quite comparable to the existing constraints that we have in for excluding out the sterile neutrinos through Dirac. Yeah. So, but one of the things that I did not talk about is the challenges that we face with respect to the background events. So, so the main problem comes with cosmic muons, which lead to the production of neutrons, which so if we do not know what those numbers are, it might be difficult to resolve between the signal and the background. So that's the very, I'm going to put that in a very simple way. Yeah, so yeah, that's all. So to conclude, so one of the good things about DLS is that it has sensitivity to both the charge current and the neutral current events, and the sensitivity that we can in principle have with a deuterated liquid scintillator is comparable to the present constraints that we have with sterile neutrino scenarios, and we still have to work on the backgrounds to get a more final understanding of the sensitivities. Yeah, thank you.
Thank you, Supra. Okay, next we have Apurva Biswas from IMSc. He's going to be talking about anomalous relaxation in non-equilibrium systems. So 15 minutes? Yes, sure. I'll give you 2-minute warning. Yes, sure.
I'll be discussing about an anomalous relaxation phenomenon that occurs in non-equilibrium systems. So I hope these two pictures will give a rough outline of my talk. So what this picture shows is these two trajectories which are named A and B, and these two start from two different points. And they are approaching some common reference point, which I have not shown here. So the y-axis measures the distance of these 2 points as they approach the final reference point. Now the question that we would be interested in is the following. So we'd like to ask if the trajectory that started from an initially further distance can overtake the another trajectory B. And we would like to ask this type of questions in the relaxation dynamics of this kind of system. So this is a single Brownian particle which is diffusing in a potential landscape. So the questions like why this kind of relaxation is anomalous and why we are calling it as a non-equilibrium system would be clear in this talk. So this work has been done with R. Rajesh and Annapal at IMSc. So let's first consider the general scenario of relaxation that comes to our mind. So we'll consider two equal volumes of water, say, which are initially heated to two different temperatures, say 50 degree and 30 degree. Now both are cooled to a same temperature Tf, which is at 0 degree, say. Now if the process is quasi-static, I mean that if it occurs very slowly, then this kind of relaxation is very well described by the Newton's cooling law. So if delta T is the difference of the temperature of the system with respect to its surrounding, then it says that the time evolution of the temperature difference is directly proportional to the temperature difference of the system with respect to its surrounding. Now in that case, if we compute the equilibration time that the system take to relax from this temperature to the final temperature, we will find that the equilibration time increases logarithmically with the initial temperature difference of the system. So in this case, we will find that the colder system, which is initially at 30 degree, will eventually cool faster compared to the system which was initially at a higher temperature. But then there is an anomalous behavior to this kind of dynamics that was first shown systematically by Pemba. So this is a simple experiment. So he considers equal volumes of water which are initially heated at different temperatures, and then he puts them to the freezer and he measures the freezing time that all the samples take. What he found is the following result. So in this curve, the x-axis is the initial temperature of the different samples that he had prepared, and the y-axis are the freezing time that the different samples take to relax to different samples take to freeze. What he found is a slightly anomalous behavior. So if you can see in this region, if you increase the initial temperature of the samples, you will find that they take less time to freeze. So after that, many experiments had been done, and they have found this kind of phenomena, but they have reported different results for the occurrence of this kind of phenomena in water. So few of them are the following. So like the presence of supercooling or the presence of impurities and so on. But then in the case of supercooling, what happens is that a liquid might go below its freezing point without even undergoing the freezing. It might be still in the liquid state. So in that case, if we measure the freezing time, that will eventually give us a large time. Similarly, in the case of impurities, it might happen that it can increase or decrease the freezing time. So due to the presence of these factors, we might get an ambiguous result for the occurrence of the Pemba effect in water. And all these reasons that I told are only specific to water. So leaving behind all these ambiguities that are the reasons for its occurrence in water, we will ask a more general question in simple setups. So consider two identical copies of a system, which can be any system of your interest, say a magnetic system or a system of molecular gases undergoing relaxation, and you prepare the systems to two different initial states. So like for the case of magnetic system, you apply different magnetic field to the two systems so that they would attain different magnetization initially. And then there is a final state F here where both the systems would like to relax. So how will you attain that? So for the case of spin system, you will apply same magnetic field to both the systems so that they attain a common magnetization state. Now note that the initial state A is initially at a larger distance compared to B from the final equilibrium state. And what we would like to ask is whether the system A, which is initially at a larger distance from the final equilibrium state, can actually relax faster. Now in this kind of dynamics, when we tune the external parameters so that both the systems reach the final state, that we do it instantaneously. So this process is called quenching. When we apply that, the system is driven out of equilibrium. So this kind of phenomena has to be studied in the non-equilibrium framework rather than the quasi-static description that I had shown earlier. Now, in order to study this kind of dynamics, what are the requirements for that? So as the system relaxes from one initial state to the final state, we would like to track the evolution of the system in terms of a distance function, which is a distance of the system from its final equilibrium state. And then if there is an existence of such anomalous relaxation, it would definitely show a crossing of the trajectories of the two systems as they relax towards the common equilibrium state, as shown in this figure. So system A and B starts from two different points. The y-axis is the distance, initial distance from the final equilibrium, and as you can see, the A is relaxing faster than B. This is just a schematic diagram. And there are certain properties that the distance function with which we are measuring the relaxation of the system, so it should satisfy certain properties. Since we are studying relaxation, so the relaxation process cannot push the system away from equilibrium. So the distance function that you define has to be monotonically non-increasing function of time. And moreover, the distance function should also mimic the initial condition that the system was initially prepared at. For example, if a system if there are two systems, one at a hot temperature and another at a cold temperature, then the distance function at time t equal to 0 for the hot system should be higher than that of the cold system. Otherwise, it can give us false realization of the Pemba effect. So with this framework, we'd like to understand this anomaly in simple setup of a single particle system, which doesn't have all the ambiguities that I had discussed for the case of water. So this system consists of a single Brownian particle. These are micron-sized particles, which is put in water. So this will experience the fluctuations due to the kicks from the water molecules. And the water is initially at a temperature TH. So this water acts as a thermal reservoir or a heat bath. And in addition, the particle experiences an external force due to this potential. And this kind of potential in experiments is achieved using the optical tweezers. So due to the confinement of this external potential, the particle is confined between these two positions, x min and x max. Although the particle position is fluctuating, due to the confinement of this potential, it will eventually attain a time independent equilibrium distribution for its position, which is denoted by pi of x comma th. So initially it is at an equilibrium corresponding to the temperature th. Now what we will do is, we will change the bath temperature instantaneously to Tb. So you can think of it like this. So you consider this setup and you attach a different heat bath to it. So the system will be driven out of equilibrium until it reaches the equilibrium distribution corresponding to the new temperature Tb. So we do this experiment several times, but in each of the time, what we will do is we will choose a different temperature for the heat bath, but all the quenched temperatures, final temperature would be the same, and we are interested in the relaxation time of the system. So in this experiment by John Bakehofer's group, they showed that there is a role that this potential plays in the relaxation dynamics. So consider this first case A over here. So this is the case where the potential is symmetric. By symmetric I mean that the domain widths of this potential with respect to the origin is equal. So in the first case, x max is equal to x min. So what they are doing is they are measuring the relaxation time as a function of the initial temperature from which the system had started equilibrating. What they found was that with the increase in initial temperature, they find an increase in the equilibration time of the system. But then they show an anomalous behavior in the relaxation of this kind of system due to the change in the potential landscape. So in the case B, they make the potential slightly asymmetric. So the domain widths are not equal now. So x max is not equal to x min, and in that case they find an anomaly in the relaxation time. So here what they showed was that if you increase the initial temperature, there is a drop in the relaxation time. If the further increase the asymmetry in the potential, there is a region where there is a drop in the relaxation, and then after that range, there is an increase in the equilibration time with the increase in the temperature. So that is a normal behavior after that. So we are interested to understand this kind of anomaly in this kind of system, and a simple model is always helpful to underpin the cause of such effect. So we consider a double piecewise linear double well potential. So the particle is diffusing in this potential, and since we are interested in the position distribution of this particle, this kind of model gives us the exact result for this distribution. So here is the protocol for the study of the Pemba effect in this kind of setup. So this is our system. We attach a temperature bar TH to this, so that initially it is at an equilibrium distribution pi p, and then there is an identical copy of this setup where it is initially connected to a different temperature bar Tc, and it attains an equilibrium distribution pi q corresponding to the cold temperature Tc. Now we quench both the system using a common temperature bath. So Tb would be the same for both the system. So, and eventually it will relax to this final equilibrium distribution. Now we are interested in the relaxation of both the systems to the common state, and we would like to ask if the hotter system can actually cool faster. So in order to track the system from one equilibrium state to another equilibrium state, we will use this distance measure L1. So it basically measures the instantaneous distribution of the system with respect to the final distribution. So there are two ways to analyze this. In one case, we look for the phase space of the system where this kind of anomaly occurs. So for this kind of setup, we can actually calculate the entire phase space where this kind of phenomena occurs, but we are not interested in that for this talk. Rather we'll look how the potential landscape and the initial temperature is playing a role for this kind of anomaly. So here I have taken two different cases for the potential landscape as shown in figures A and C, and in figures B and D they show the population distribution of the Brownian particle in this potential landscape. So the blue one corresponds to the population distribution of the Brownian particle when it was initially equilibrated at the cold temperature. Red one is for the hotter system, and the black one corresponds to the final distribution where they would like to reach. So in the first case we have considered a potential landscape which has a significant barrier height between the two wells. Now in this case, when we look at the population distribution of the Brownian particle, we find that the colder particle has a slight localization in the minima, local minima. So this much population has to hop over the barrier in order to attain the final equilibrium state, and this relaxation due to the thermal process is very slow. On the other hand, the hotter particle, if you look at its population distribution, it has a uniform distribution over the entire landscape. So it says that it doesn't feel this potential landscape, and it can relax to this final equilibrium much faster than the colder one. That's why we see a Pemba-like behavior in this case. On the other hand, if we consider a flat potential, so there is no such barrier height between the two wells, and in this case, if you look at the population distribution of the Brownian particle, you find that they have a similar distribution. And since the colder particle is initially closer to the final cold temperature, it relaxes faster, and we do not see such anomalous behavior in this case. So the presence of a high barrier is actually playing the role of a metastable state, due to which the colder particle is cooling fast, the hotter particle is cooling faster. So just 1 minute. Yeah. So we are also interested in some in microscopic parameters that can actually capture this kind of relaxation, and we have also done some analysis in many particle setups so which we are not discussed, but it is highly counterintuitive in this case because there is no such metastable state in this case. And this kind of setup will might have possible practical applications also. So this was done with Prasad, Oren and Rajesh. And so this kind of study for the anomalous behavior would certainly be interesting because this can lead to better understanding of better understanding of the relaxation behavior in non-equilibrium systems. So with that, I would thank you for your attention.
So next we have Vinod Mamale. He's going to be telling us about effect of fluctuations on symmetry and fields. So we'll finish in 15 minutes?
I will try.
Okay, I'll give you a 2-minute one.
Hello. So today I will be talking about effect of fluctuations on symmetry and fields. So which symmetry and which fields we will see. So any physical system is not ideal. So there will be some fluctuations in it. That the type of fluctuation can be there thermal fluctuation, quantum fluctuation, or mechanical fluctuations, or any other type of fluctuations. So these fluctuations can lead to many interesting effects such as spontaneous breaking of symmetry, Casimir effect, or other kind of effects. So every time when there are in physical system, we usually have the competition between extremization of action or energy. So system tries to minimize the energy as well as tries to increase the entropy. So there will be competition between that. So today I will be talking about three such effects. One is one will be thermal fluctuation, which lead to realization of Z symmetry, and this in turn changes the nature of confinement deconfinement transition. The other thing is effect of thermal fluctuations on mechanism of topological defect formation, and the third thing is mechanical effect of mechanical fluctuations, such that gravitational waves drive the parametric resonance in non-abelian gauge fields. So first one, the thermal due to thermal fluctuations, realization of Z symmetry, and nature of confinement deconfinement transition. So at finite temperature, bosonic and fermionic matter fields satisfying only periodic and anti-periodic boundary conditions contribute to the partition function. So this breaks the Z symmetry of the action. So here we are considering only SU3 Higgs, so it breaks the Z3 symmetry of the action. So we are considering SU3 Higgs in fundamental representation, and we study it near the CD transition temperature. So the partition function function has two parts. One is one which has the Z3 symmetry, and other one which breaks the Z3 symmetry. So the pure gauge part as well as other than Higgs gauge interaction term, other terms have the Z3 symmetry. Only the Higgs gauge interaction term breaks the Z3 symmetry. So we work with this lattice version of this, and we do this in Higgs symmetric phase, because in Higgs broken phase the Z3 symmetry is explicitly broken. So in principle, when one integrates out the matter fields and the special gauge fields, one would expect that partition function can be written in terms of Polyakov loop, which is the order parameter of CT transition, and there will be action will act as a Boltzmann weight, and there will be density of state. So this G of L, it is Z3 symmetric, as well as it depends on n tau, and n tau is number of time steps. So it increases with n tau. So at fixed temperature, higher n tau corresponds to approaching continuum limit. So this higher n tau leads to higher GL, and so we will see that density of state dominates the compared to Boltzmann weight, then density of state will dominate, and we will see the restoration of Z3 symmetry, which was broken even in the action. So that's how the Z3 symmetry is realized in the continuum limit. So here we have two plots of at n tau equals 2 and n tau equals 4. So we see that for n tau equals 2 we have expectation thermal average of Polyakov loop, and we see that the nature of transition is crossover, whereas when we go to n tau equals 4, we see that it changes to the first order phase transition, and that as n tau equals 2 we have limited GL will be small for n tau equals 2 and GL will be larger for n tau equals 4. So that is the effect of density of states. So to verify this, we have also done comparative studies to see that it's actually the effect of density of state. We have done comparative studies with Z2 Higgs, as well as we have done analytical calculation of one-dimensional chain with the SB part of the action, and that was done for general SUN as well as for Higgs. So we have verified that in both the cases we have verified that density of state is the responsible for this restoration of Zn symmetry. So the second problem we are talking about is effect of thermal fluctuations on the mechanism of topological defect formation. So Kibble-Zurek mechanism is used to give a theoretical description of topological defect formation. So it has two postulates. One is that there are formation of domains, and the second one is that geodesic rule. So formation of domains says that there will be the order parameter will be uniform in regions. So these represent different domains. So order parameter will be uniform in this, and when here we are considering order parameter space to be circle, and when it winds non-trivially, we will get a topological defect, which is at the collision of the different domains. So like these are topological defects will be formed there. So that is the first postulate, and the second postulate is geodesic rule, which says that from here to here, when order parameter traverses from here to here, then because it should change slowly, otherwise the gradient of field will contribute to the energy. So it will cost larger energy when it traverses longer path. So example here we have, if we consider these two domains, we have considered the possibility of how the order parameter changes from in between those two. So it is possible that it changes like this, which is which leads to minimum energy, and so it is the geodesic path, and the other one is it takes longer path, and also there will be other possibilities other than these two also, where the order parameter winds around and gives non-trivial topology, but So all of these possibilities are there. So now, so there are like competition between like, as one decreases the temperature, the fluctuations will decrease, but at the same time, the correlation length increases as one approaches critical temperature, and as one is approaching from above, that whether the fluctuation will decrease faster or whether the domain size will be getting larger. So what happens to the geodesic rule? So we see that most of the time geodesic rule is violated, and it depends on what is your quench rate and where the system gets frozen. So this is the density defect density, and it's found, according to Kibble mechanism, is proportional to xi correlation length when the system freezes out. So we see that we have done for 2D model and 3D model, we see that number of defects are like simulation estimates that it will be very, very larger compared to the Kibble-Zurek mechanism estimate. Same for 3D as well as 5-4 theory, which we have studied. So this is because we see that geodesic rule is violated very, very by very much large percentage, and so fluctuations fluctuation result in higher number of defects in both of the 2D model and 3D model. So the third thing is that we consider fluctuations, periodic fluctuations in space-time, which lead to parametric resonance. So it was previously seen that space-time oscillation generate parametric resonance in matter fields. So we wanted to study what will be the effect of such fluctuations on non-abelian gauge fields. So we have considered small periodic space-time fluctuation on top of Minkowski background. So why this particular background is considered? Because this mimics the plus polarized gravitational wave traveling in the z direction. So this leads to this equation of motion for non-abelian gauge field, and we can see that when we go to the linear approximation, this is same as Maxwell's equation with the in this metric background. So we analyze these equations for and evolve those equations, and we studied the different modes of those fields, and in linear approximation we find that these are the equations for those modes of those fields, and these are for A1 and A2 and A3. So these clearly have f of t, which is also a periodic function of periodic function in time. So we see that these equations are give rise to parametric resonance. So these fields will show a very large increase, and so this results in increase in energy density also. So this plot is here is energy density versus time, and this energy density non-abelian versus abelian. So we have plotted the difference only, and we see that as time goes on, the difference goes on increasing. So as we can see, this is log plot, and even the slope of this thing changes. So it's like a very strong increase in the energy density. So we see that non-abelian have more increase in energy density compared to abelian gauge fields due to parametric resonance. So another thing is we want to study the CP violating term E bar dot B bar, how it will evolve due to parametric resonance. So we see that E bar dot B bar in linear approximation results to this condition, and even if you look at this condition, it depends on A3 dot by A3, which when one looks at this equation, these two are different equations, as A3 is coupled to A0 as well as there is some extra term of rigidity. So even if at t equals to 0, if this equation is satisfied, it won't be satisfied at later times. So we study when FF dual term in like non-abelian we consider FF dual term, and we see that parametric resonance leads to larger values at later times as shown in the figure. So this figure we have in x and y, we have plotted the contours of FF dual, and we start with FF dual to be 0 initially. At the center we consider a Gaussian, and we see that it eventually evolves and spreads in the space, as well as the value gets increased. So we see that gravitational waves can result in different effects and parametric resonance in non-abelian gauge field. So in overall, we have shown that thermal fluctuations lead to Zn symmetry, and thermal fluctuation can also result in change in affect the KZM mechanism, as well as it can like mechanical fluctuation of like gravitational waves passing can also generate parametric resonance in non-abelian gauge fields. So thank you.
Thank you very much. You finished exactly on the dot. Okay, Sunil Naik, he's from IMSc also, and he's going to be telling us about Ramanujan tau function and its prime factors. 15 minutes.
Good afternoon, everybody. I'll speak about Ramanujan tau function and its prime factors. Let n is equal to 1, 2, 3, 4 be the set of natural numbers. A natural number p is called a prime number if its only positive divisors are 1 and p itself. For example, 2 is a prime, 3 is a prime, 5, 7, 11 and this big number are prime numbers. And we know that there are infinitely many primes thanks to Euclid. From fundamental theorem of arithmetic, we know that any natural number n greater than 1 can be written uniquely as a product of primes, and can be written as p1 to the power a1, p2 to the power a2, pr to the power ar, where pi's are distinct primes and ai's are natural numbers, and r is exactly equal to number of distinct prime factors of n. So let us introduce the following notation. Omega of n equal to number of distinct prime factors of n. We put omega of 0 and omega of 1 is equal to 0, and we extend this notion to negative integer by simply putting omega of minus n equal to omega of n. For example, omega of 6 is 2, since 6 has exactly 2 prime factors 2 and 3. Omega of minus 350 is 3, since 350 has exactly 3 prime factors 2, 5 and 7, and omega of p is 1 for any prime p. We are interested in estimating the size of the number of prime factors of n, omega of n, by using the prime factorization and noting the fact that the smallest prime is at least 2. So we get n is at least 2 power r, which is precisely 2 power omega of n. By taking logarithm on both sides, we get the following upper bound. Omega of n is bounded above by log n by log 2. In fact, with a little more effort, we can show that number of prime factor of n is bounded by log n by log n. Here, this notation less than implies that means there exists a positive constant c such that omega of n is bounded above by c times log n by log n. So what about the lower bounds? In order to produce the numbers with large number of prime factors, an obvious way is to take the product of primes. In particular, let m to be the product of all the primes which are less than or equal to n. Then by using the prime number theorem, which actually counts the primes up to large number, we can show that this natural number m has at least log m by log m prime factors. Hence, this bound is the best possible up to constant c. In this connection, Hardy and Ramanujan in 1917 proved a remarkable result they show that number of prime factor of n is of size log n for almost all n. Almost all in the sense the set of natural numbers n such that omega of n satisfy this inequality has density equal to 1. We can also ask the same question for other interesting sequences in number theory, for example, divisor function, Euler-Torsson function, etc. So, we are interested in a function which was introduced by Ramanujan in a seminal paper of 1916, namely Ramanujan tau function. Let me define it. Consider the infinite product, x into product n is equal to 1 to infinity, 1 minus x power n to the power 24. Expand as a power series in x, we get x minus 24x square plus 252x cube, so and so on. So, we have tau of 1 is 1, tau of 2 is minus 24, tau of 3 is 252, tau of 4 is minus 1472 and so on. If we consider the function delta equal to summation tau of n times e power 2 pi I n z, where z is a complex number with positive imaginary part, then delta is the simplest example of something more involved what are called Hecke eigenforms. These Hecke eigenforms are special cases of modular forms, objects that are central in the development of number theory in the second half of 20th as well as 21st century. For instance, these objects are crucial ingredients in Weil's proof of Fermat's last theorem as well as formulation of Langland's program, a theme which dictates the trends and trajectories of large parts of modern number theory. Before moving on to our question, let me state that Ramanujan made the following predictions regarding tau function. The first thing is that tau is a multiplicative function. That is, if you take two co-prime natural numbers m and n, then value of tau at mn is equal to tau of m into tau of n. Values of tau at prime power satisfy this beautiful recurrence relation, and he predicted that the following interesting upper bound for the absolute values of tau of p. First two properties were proved by Model, and the third property was proved by Deligne as a consequence of his proof of the Weil's conjecture. Let us come back to our question regarding number of distinct prime factors of tau of n. The first question is whether there exists a natural number n for which tau of n equal to 0, because if tau of n equal to 0, then by definition omega of tau of n is 0. So, we are interested in the set of natural number n for which tau of n not equal to 0. What can you say about this set, whether it is a finite, infinite? In 1947, Lemma conjectured that this set is equal to whole n, that is, for all n, tau of n is not equal to 0. He himself verified this conjecture for first 214 billion numbers. Later, this was improved to 10 power 15 by Serre. Up to the best of my knowledge, we know that tau of n is not equal to 0 for for n less than or equal to approximately 8 into 10 power 23 numbers. This is due to Derricks, Winos and Zeng in 2013. Okay, let me make the first attempt towards estimating the number of prime factor of tau of n. The one way is to get a upper bound on the absolute values of tau of n, and I use the upper bound for the number of prime factor to get a upper bound on the number of prime factor of tau of n. Using purely complex analysis, Hecke proved this remarkable upper bound for the tau of n. Absolute values of tau of n is bounded by n power 6, even though better upper bounds are known, and this is sufficient for our purpose. Using the Hecke's bound and the upper bound for the number of prime factors of n, we have the following upper bound for the number of prime factors of tau of n. Omega of tau of n is bounded above by log n by log log n. So, what about the lower bounds? Can omega of tau of n equal to 1? This is equal to saying that tau of n is a prime or a prime power. Even we can ask the more harder question, can tau take prime values? Indeed, the answer is yes. This is due to Lemma. He showed that if you go all the way up to 63,000, you would get a prime value. The value of tau function at 63,001, this big number with 26 decimal digits, is actually a prime number. We know that tau of p is even for all primes p. This can be proved either using Jacobi's triple product identity or theory of Galois representations. Serre in 1976 proved that 2 is a particular case. He proved that for if you take any natural number d, tau of n is divisible by d for almost all n. And recall that we have seen omega of n is of size log log n, that is a random integer n has log log n prime factors. Whether the similar bound is known in case of tau function. This was proved by Murthy and Murthy in 1984. They show that number of prime factor tau of n is of size log log n whole square for almost all n. provided the generalized Riemann hypothesis is true. In 2006, Luke and Spelunky deduced an unconditional lower bound for the number of prime factors of tau of n. They show that tau of n has at least 1 minus epsilon log n prime factor for infinitely many n. In a recent work, we improved this lower bound to 2 power 1 minus epsilon log n divided by log n for infinitely many n. The way it's stated, it may not be clear why this is an improvement. Let us take the logarithm on the both sides and compare the lower bounds. Result of Luke and Spelunky gives the log of number of prime factors of tau of n is as big as log n for infinitely many n. Our result shows that log of number of prime factors of tau of n is as big as log divided by log n. In the result, we have 3 logs. In our result, we have 2 logs divided by 3 logs. From the analytic number theory point of view, both are of different order of magnitude, and this is a genuine improvement. Our result unconditionally shows that earlier bound of Murthy, which is under GRH, is actually optimal, in the sense that in the result, almost all cannot be replaced by all but finitely many n. Let me come to the final part of the talk. We have seen that tau of p is even for all primes p, so they are not expected to be primes. So we can ask what can you say about the largest prime factor of tau of p, or more generally, what can you say about the largest prime factor of tau of p power n? In a recent work with Shaoli-Gun, we proved that for any n greater than or equal to 2, for any epsilon positive, the largest prime factor of tau of p power n is at least log p to the power 1 by 8 times log p to the power 3 by 8 minus epsilon for almost all prime p. This is a result towards a non-Archimedean analog of a question of Atkinson, which I am not going to state due to lack of time. And in another recent work with Uribilu and Shaoli-Gun, we proved that the largest prime factor tau of p is at least log p to the power 1 by 8 log p to the power 3 by 8 minus epsilon for almost all prime p. Both these results require different technique, and both the results are best known in this direction. Thank you for your attention.
Thank you. So you finished earlier. Is there any question? Anybody? There's a question.
You may not like my question, but it's not meant to hassle you, okay? That in what application context do you think results like this are relevant?
So, the first thing is, first of all, one way is to application the cryptography, because in the cryptography we need the large number of prime factors. So therefore, one way, since we know that by the conjecture of Atkinson, we know that the absolute values of tau of p is as large as grows like a polynomial time, and also symmetries. So therefore, we can also same question whether this can be used as like prime producing machines. The values of tau of n can be used to get the large primes for which can be used in the cryptography as well. And also this modular forms.
Is useful. I mean, this is a bound, so it can be useful in many contexts.
Yes.
Yeah. So any string of symbols, for example.
I did not get you.
Any string of symbols. Any string of symbols. Okay.
Okay.
Okay. For any string of symbols, if you can see what can be a bound on it and what kind of symbols, this may actually, I don't know. Maybe you should talk to the computer scientists. It might actually have an application.
Sure.
Yeah.
One more question, if anybody has. Okay, looks like not. Thank you very much.
Thank you.
Not working. Oh, you're already here. Okay. How are you doing? 15 minutes, and I'll give you a 2-minute warning. This mic is not working. Okay, the last talk of this session is by Nirmalya Kajuri from IIT Mandi, and he's going to tell us what he's going to be talking about.
Okay, first of all, let me thank the organizers for this opportunity. And I'm going to talk about black hole information loss, some recent developments. So I won't be talking about my work at all. I will review some of the recent developments in this field. So everything, all of physics that we know is governed by quantum theory. However, in the presence of black holes, quantum theory seems to fail. But recent results from ADS-CFT duality show how quantum theory might be rescued. So that's what we are going to talk about. Okay, so let me go over some basics of quantum theory that most of you know. Quantum theory does not tell us how to predict the outcome of a single experiment. However, it does give us probabilities of predicting different experiments. And all these probabilities are encoded in a mathematical object called the quantum state. Knowing the quantum state, you know all the possible probabilities of all the possible measurements. And when I talk about quantum information, I'm talking about information of this state. Now, it can so happen, one of the unique features of quantum theory is that we can have the phenomenon of entanglement, which is when quantum information is carried by two or more systems in a collective way. So you need to get hold of both the systems to have the quantum information. And an analogy is this jigsaw puzzle. So take this two-piece jigsaw puzzle, and we need to have both the pieces to get the full information. If we have just one of the pieces, we don't have the full picture. And I'm going to really lean on this jigsaw puzzle analogy throughout the talk. Okay, so what is the paradox of the black holes? And this goes back to Stephen Hawking, who said black holes give out radiation, and you won't believe what happens next. He didn't actually say that, but that's what his work showed. So what did Stephen Hawking actually show? He showed in 1976 these two things, that black holes radiate, and this radiation is highly entangled with the black hole. So this is the picture of what happens. We have a black hole, and it radiates. And this is the photon coming out, and this is highly entangled with the black hole. So I have represented with two pieces of the jigsaw puzzle. And as more and more radiation comes out, more such jigsaw puzzle pieces are being generated, which means that if I'm outside the black hole, if I'm an observer who is outside the black hole, I only have access to these red pieces, not the blue pieces. So I don't have access to full information. I only have access to part of the information. All these blue pieces represent missing information, information that is missing from me. That in itself is not a problem. Quantum mechanics does not tell us that we should have access to all information. However, the principle of unitarity of quantum information says that information cannot be destroyed, which means that, translated to the jigsaw puzzle picture, that the number of red pieces and blue pieces have to be the same, so that they can all fit together. And this principle seems to be violated in this way. So this is the picture of what happens when a black hole radiates more and more. So as the black hole radiates more and more, it loses energy via radiation, and so it shrinks in size. And more of this missing information pieces are being generated. So in the second picture, you can see that now the black hole is smaller, but it also now contains more missing information in the form of these blue pieces. But ultimately, as the black hole keeps shrinking, it will evaporate. It will disappear completely, taking all the blue pieces with them. And we would be left with this red incomplete pieces, which means information just disappeared. Information is lost, which was exactly what unitarity said should not happen. So this is the summary of what we just saw. The principle of unitarity said quantum information cannot be destroyed. However, black hole evaporation seems to have just destroyed the information when the black hole evaporated. So what should have been the picture according to unitarity? To save unitarity, we should have something like this. When the black hole evaporates, as it shrinks, as it gets smaller, it must start leaking out some of the hidden information. These blue pieces must start coming out as the black hole gets smaller. And in the last picture, all the blue pieces are out, and they have joined with the red pieces, so all the missing information is out. So this is what we expect should happen to save unitarity, that all the information that is hidden in the black holes has to come out, and in the end, when the black hole is gone, all of the information should be outside to save unitarity. However, this is not what the computation showed. What Hawking's computation showed was the last picture where information was getting lost. So this whole picture can be made quantitative via the quantity of entanglement entropy, which is a measure of entanglement. And in our picture, you can think of this as a measure of the number of red pieces which are not joined with some blue pieces. So these are the pieces which are not joined together. And for the unitary picture, this was the, for the unitary evolution, this was the last picture where all the pieces came out. So initially, the number of red pieces would increase, and then towards the end of the evolution, the blue pieces would come out. And so finally, the entanglement entropy, which was measuring the number of red, single red pieces, goes up and then finally goes down. This is what unitarity demands. But what Hawking's computation showed was what we saw in this previous picture, which is that the number of red pieces kept increasing till the black hole completely disappeared. So that is the second graph. The entanglement entropy increases, and then it saturates when the black hole completely disappears. So the challenge was to get the first graph, whereas semi-classical calculations were giving us the second one. And in recent years, ADS-CFT duality has come to the rescue. So what is ADS-CFT duality? This is captured by the picture here. So you see these cans of juices, and on these cans, there are pictures of what you can expect inside. So you have all these pictures of the fruits, which are telling you what kind of flavor you will get. So the first one is orange flavored, and the second one is apple flavored, and so on. And this is encoded in the pictures on the surface. And ADS-CFT is not too different. Here we have a boundary surface on which there's a conformal field, some theory, conformal field theory living on the surface. And it is exactly telling us what kind of physics we can expect from the inside. So the inside part is a space-time called anti-de Sitter space-time, which can contain the black hole and so on. And the physics of it can be also described from the boundary, from the conformal field theory living on the boundary. And the precise statement is that there are certain quantities that you can calculate in the quantum field theory living in the boundary and in the anti-de Sitter space inside, and these quantities would match exactly. And one of these important quantities is, in fact, entanglement entropy. And this is supposed to be, this is proposed to be equal to a particular area which we can calculate in the inside, in the anti-de Sitter space. So the original proposal goes back to Ryu and Takanagi, and it has been developed over the years. And the key point here is that there is a certain optimization of area calculation one has to do to find the entanglement entropy of the boundary theory. And this can be utilized now to show that we can actually get the unitary curve for the entanglement entropy. Okay, so what was the setup? So this was work done started in 2019 by Almeida et al., Jeff Pennington and others, and this has been a key development in the black hole information paradox scene. So this is about how to get the entanglement entropy curve from this ADS-CFT. So one of the problems working with black holes in ADS-CFT was that because of the boundary, because ADS space is actually like this can of juice, it's like a thermos flask which has a boundary and it reflects back all the radiation, it did not allow black holes to evaporate because it sent the energy back to black holes. So the strategy was to couple this to a bath, to put the ADS in a bath and make the boundary transparent. So what you can see in this picture is the radiation is going to come out into the bath from the ADS space. So this blue box is the ADS space, the big black box is the bath, and the circle in the middle is the black hole sitting in the anti-de Sitter space, and it's radiating. And the radiation is going out and getting collected in the bath. So, so the idea of the calculation is now to use ADS CFT to track entanglement entropy between the bath and the ADS and the boundary, which is proxy for the ADS space. And this calculation serves as a proxy for calculating entanglement between the radiation that's coming out and the black hole. So what's the answer? So we get exactly this answer, that we can calculate this exactly at early times and at late times. And it turns out that at early times, the entanglement entropy grows exactly as Hawking's calculation showed it would. But at late times, the answer is very different from Hawking's calculation. The entanglement entropy is seen to go down, decrease, and go to 0, which is exactly what was demanded by unitarity. So it turns out that the computation from ADS CFT using the duality and the latest prescription for entanglement entropy, one actually does get the unitary page curve. So unitarity is being restored. And so how is this happening? This can be kind of understood through this picture, is that what happens at late time. So you see in this picture, there's a blue region, which I've named the island, which contains the black hole. And what seems to be happening at late times is that, so first of all, at early times, the picture seems to be exactly the same as the old Hawking's picture, which is this. Radiation is coming out and so on. But at late times, there is this region called the island which emerges, and this region is secretly outside, which means that all the information in this island region is shared with the outside. So in a sense, all the information that is in this part within the black hole is also present outside. So all the blue dots, all the blue pieces are also present outside. So you can see outside of the black hole, the number of blue and red pieces are the same. So all the information is actually out. So the interior of the black hole somehow got encoded in the radiation, and all the information came out at late times. So this is the picture that emerges from the recent computations. However, there remain some open questions. It's not clear how the information escaped. It's not clear how what I said happened, how the information inside got encoded in the radiation outside. The mechanism is unclear. So that is one of the things we would really like to know to say that black hole information problem has been solved. And then attaching a bath, as we did, with the ADS space. And what we do is we demand that this bath does not have gravity. This is important for the calculation, for the bath not to have gravity. But this leads to certain problems. Particularly, this shows that the theory of gravity acquires some mass. It becomes massive gravity. And so there are certain problems associated with it, which have been pointed out by Subrathraju, Andreas Kirch, and others. And they have their own proposal of called holography of information, which is an alternate possibility, which says that, contrary to this, which says that the information is always outside in the boundary, and it is never lost. There is never, the page curve is a flat line. So it is never increasing or decreasing. So this is a different proposal, which also has quite a few things going for it. And in the future, we hope to resolve these issues and figure out how to resolve this tension between bath with no gravity and information loss, and also how holography of information fits into this picture. So thank you for your time.
So we have a little bit of time left. If you have a quick question, maybe anybody. Yes, there is one question.
Yes.
The black hole is
You've drawn this black hole inside the island. Is
Yes.
that how it should be?
Yes. The island region is bigger than the black hole. So it contains the black hole, but it's strictly bigger than it.
Okay, so let's thank Nirmali again.
So there is a small announcement. One second. Yep. So we will start at 2:50.